this is all about. My name is Dan Buscombe. I am currently a consultant contractor for the US Geological Survey, Coastal Marine Geology Division in Santa Cruz, and formerly a professor at Northern Arizona University. But prior to that, I was a geologist working at the Grand Canyon Monitoring Research Center, which is a USGS office in Flagstaff, Arizona. And I got into machine learning methods. I was sort of an early adopter of some of the methods that were being used for seafloor characterization. And so I sort of got into machine learning methods using bathymetry and backscatter data back in 2012. And then from there, I've sort of developed workflows using various types of machine learning algorithms for various types of problems in geology and ecology, using sort of imagery primarily from drones and airplanes, and some work with satellite, and also a lot of work using machine learning workflows with submarine and sort of subaqueous platforms and subaqueous data. So don't have a background in computer science. My background is in geography, geology, and oceanography, and I imagine most of you have similar backgrounds, and that you're sort of coming at this from a similar perspective to me, hopefully. Obviously, the workflows that you're going to see today, they're very specific to a particular data set, also very specific in terms of they've been written by myself and not too many collaborators so far, but also the specifics of the model and the various training strategies that we sort of use with the model. But hopefully along the way, I'm going to highlight some of the areas that there is room for extension, and replacement of various workloads. So even though the workflow is obviously going to be very specific data and the particular choices that I've made about workflow, hopefully I'm going to impart a few general concepts that you can sort of take home and sort of start developing, using some of the materials as well. Kind of difficult figuring out how many people are actually going to show up to this. We currently have 44. I guess I'll just give it another couple of minutes, and then I'll just sort of get going here. But if anyone has any burning questions or big issues with accessing the materials or anything like that, then I guess now would be a good time to unmute yourself and let me know. And I'll assume if you're all silent, I'll assume that you managed to get onto the website that I made for this, and then you managed to navigate to the Google Colab from there. Okay, so I'm going to go ahead and share my screen, and hopefully you see my web browser. I've just got one eye here on my participants because I need to let them in as they come in. All right, so welcome everyone. I gave the spiel of who I am. I'm Dan Buscombe. I work for, I'm self-employed nowadays, but I contract for the US Geological Survey, and I'm formerly a professor at NAU. My background is not computer science or particularly remote sensing, but I have sort of gravitated towards both those topics over the course of my career. And in particular, I'm sort of very, very engaged with developing workflows for applying sort of machine learning, sort of state-of-the-art or established machine learning sort of algorithms, and I like to apply to the science problems that I'm working on. And I've worked both above water and below water. A lot of the work that I've done with machine learning started out in the fluvial world, looking at bathymetry and backscatter data and trying to sort of use machine learning processes to convert that into useful products for us. And then I'm sort of now in the process of translating some of those workflows and ideas and application over to subaerial remote sensing. And my particular interest is coastal remote sensing, in particular hurricane impact. And so a lot of the workflow that I'm going to be showing you today has been researched by myself, but it's using models that weren't originally developed by myself. They were developed by computer scientists working at sort of the low-level algorithm development. And what you're going to see today is an example of how you might take a sort of sophisticated machine learning algorithm or workflow and sort of adapt that towards your own purpose. So we've got 46 people here. I'm going to keep admitting people as they show up. Everyone's muted, or everyone should be muted at this point. If you're not muted, please mute yourself. I will be fielding questions as we go. You are welcome to ask a question at any time. Please ask questions, because otherwise it's going to feel really weird for me speaking to my computer to make you out. So I really hope that you're able to engage with me, ask questions, and we can have sort of a stimulating conversation as well as demonstration. All right. One more person to admit. Right. So this is where, yes, we are being recorded. So for that reason, if you can keep your questions sort of concise and to the point, that would be ideal for anyone who's listening to this afterward. I don't actually know what system has planned for the recording, but I believe it will be edited and posted on the system's website, perhaps, so it will be made public.
That is correct, Dan.
Yep. Thank you.
And the other thing I'd like to mention is that all of these materials I've made public through this website. I haven't yet advertised this particular website that you're looking at because I wanted all of the systems folks to get first dibs on this stuff, but also because I really want your feedback, and I'm hoping to use what I learn today and tomorrow to keep evolving this workflow material so it's sort of useful. And then as soon as I've got it to a point that I'm happy with, I'm going to sort of broadcast it more wide. So these materials and more actually will be available through these means. Okay, so hopefully you got to this point here and you saw this website, you saw the email with the instructions, and that this isn't going to be too much of a surprise. But I'm just going to go through this. I want to start by thanking US Coastal Marine Hazards and Resources Program and the USGS CDI community for supporting me, and also for Systems, obviously, for inviting me. I actually did a systems clinic, not workshop, clinic. I did a systems clinic last year, and it was a lot of fun. And I think a lot of people got something out of it, and so they asked me back. And this time I asked for 2 slots because I wanted to talk a little bit more detail about some of these models and have a bit more time to answer questions and to talk through people's sort of specific ideas. So here we are. So hopefully you're here because you've signed up for both courses, but obviously these materials are available online. So if you don't feel like you need just to listen to me talk, then you still have access to these materials. And so this is for anybody really who's interested, anyone who's a sort of a professional scientist, especially geology, they have need of image citation. So I put together I've researched and put together a workflow that seems to work fairly well for sort of generic segmentation problems, at least ones that I've been working on. And the particular workflow that we can see today is harnessing a model called UNet, which is a deep learning citation. But I found that this particular UNet that I've adapted, it seems to work fairly well for lots of different types of image segmentation tasks. So that's why I'm sort of confident in presenting this stuff to such a diverse group, because I think a lot of folks might find utility. And so I feel like I can say that because I've used this particular model for big scale stuff, segmenting lakes and seas and things like that from large format imagery, like satellite imagery, relatively low spatial resolution imagery, but also very close range photography too, all the way down to very, very close range photography. So there's something about this particular model that I think works fairly well for natural sciences in particular, and I'll talk a little bit about why I think that is. That's not to say, though, obviously, that this is a generic workflow that transfers perfectly to any problems or tasks. Obviously, but still, I think there's something in this model that a number of might find useful. Trying to admit one. Okay, so we're up to 49 people now. Apparently, there's still another 20 people to show up, but I'm guessing we're converging to a point where there's no more people. So the prerequisites. This is a fairly involved workflow in some respect because it has a lot of Python code in it. It needs a lot of Python code to work because a lot of that Python code is sort of wrangling the data, and that's a big part of what I want to present here. Machine learning is all about data. It's not so much about the model, even though a lot of models get promoted as being these generic models, like I just did. It really is also about understanding your data and having enough programming ability to coerce your data or to get your data into a format that's amenable to a machine learning work. And in particular, deep learning, we'll talk a little bit about a few of those considerations for taking these materials and applying to your, and hopefully you can ask me a lot of questions about. But if you're, I'm hoping that you all have at least some familiarity and experience with Python. This is, as I say, it's a pretty Python heavy workflow, and if you get lost along the way, then it might be because there's a particular Pythonic thing that's not being understood. And if you can communicate to me that during the workflow, then I appreciate that. I'm trying to evolve. Is this the first time that I presented these materials too? So any feedback that you have. What else did I want to say at this juncture? So we're going to be using Jupyter, which is it's going to be a convenient way for us to go through the materials using Google Colab, which is essentially an online, free to use online cloud computer that hosts Jupyter Notebooks. Jupyter Notebooks are notebooks that contain both Python code as well as rich text and video and media and other things in order to sort of wrap your code into a way that is easy to teach and collaborate. But if you're doing deep learning on your own data, on especially very large data sets, then the onus is on you to essentially adapt these workflows to a desktop computer. I've deliberately strayed away from that in particular for this systems class because there's still the installation of Python and the updating of various libraries and having environments that are clean and are sort of useful for you and are not going to break. That's actually a fairly different thing if you're especially if you're starting out, and that can be a big barrier to it's a big significant barrier, especially at deep learning. So Google Colab is going to be a really useful. All right, let's get on. I want to go straight to this. This first lesson is what we're going to be spending the rest of our time on. I did provide a getting started with TensorFlow, which is what you're looking at on this screen here. Hopefully, a few of you who have no experience with TensorFlow managed to get to that and go through that workflow. That workflow is very similar actually to a number of different tutorials that you find online. I link to a few of those in the course website. So if you are struggling with some of the concepts and some of the syntax, then I would encourage you to sort of go back to maybe that particular tutorial or go to one of those. But I'm not going to be starting with this because I'm going to assume that you have a basic grip of TensorFlow, and we can start here, which is day one, constructing a generic image segmentation model. Okay, so anyone have any questions, burning questions before I begin? You're just eager to get on with it. All right. So before we get started here, I'm just going to sort of go through what it is that we're going to be doing and what it is that we're not going to be doing. We are going to be constructing we're going to be working through a particular workflow that I've put together and researched that works well for segmentation in general. It especially works well for binary segmentation. And what I mean by binary segmentation is segmenting or classifying every pixel of your image, segmenting your image into just two classes: the class that you're interested in, and for us, for this first part, that's vegetation, and then against the background of everything. That isn't necessarily the most state-of-the-art way to do image segmentation for in particular for segmentation tasks that require multiple classes. That type of segmentation is called multi-class segmentation, where you have more than two categories. And so obviously that's where the state-of-the-art is. But I wanted to start with a simpler workflow for the purposes of the introductory nature of this work, but of this clinic, but also because I wanted to discuss, and in particular philosophy that I have is that binary segmentations actually are a great way to start any type of segmentation, because you don't always know what classes you need, what classes are going to work, what classes are actually identifiable by a human and consistently identifiable by a human. And so it's better to start off with treating the segmentation process sort of a series of binary decisions. And what I mean by that is if you have a particular data set and you have particular needs of that, you need to segment out a particular thing in your image because you need to enumerate it, you need to track over time, whatever. The other classes that you don't care about might be you may not need actually to segment them out explicitly. They might just all fall into a background class that you really don't care about. And sometimes that's advantageous because you have one particular class that you're interested in that's very distinguishable against all of the everything else. But you may run into situations, obviously, where the thing that you're interested in could be confused with something else, and so you would need to determine at what point these two things are treated separately or together by the model. And if that's not apparent at the moment, hopefully it becomes apparent as we go. So I'll keep reiterating. So in this first part, we're going to be using a data set that's public. It's out there called Error-Escape. Pretty good in that it has it's fairly relevant to us in a couple of different ways. It's not sort of it's not an ecological or a geological data set by me, but it does have a lot of the land cover and classes that you see for especially maybe so we're going to be using that. It's also because it's public, freely available. It doesn't sort of interfere with anyone's research program, and it's a good data set to play with because of the number of images and the number of classes. And also later on, we're going to be using another similar data set called the semantic drone data set, which is another publicly available data set that's used by folks to develop methods to benchmark things like that. It's not necessarily used for any specific purpose, but it does, for our purposes, have a lot of the same classes, and it's a good case study of how we might transfer what we've learned from one particular data set in terms of a segmentation over to another. And that principle of transfer is something that may come across and demonstrate. So the next sort of half an hour or so, 40 minutes, we're going to be going through the basics of how to set up a model, how to build a model, how to train a model, how to test a model, and then the last part we're going to be going over how to then take what we learned from that and apply it to a data set. If it wasn't already apparent transparent to everybody. There's no need to actually install Python on your computer. We're going to be working through just this notebook that you see up on the screen today. But obviously, if you did need to install Python on your computer to do this, then I'm available at the end to troubleshoot some of that issue. What else do I need to say here? This juncture I've covered. The main input, the main thing that I'm trying to get across here is that even though there are many tutorials that you might follow about TensorFlow and toy sort of examples, where there's relatively few working examples, sort of nuts and bolts examples of how you might get one of these models to work real, and that's obviously we count commonly in ecological application. So that's really what I focused on. This workflow doesn't give you a complete understanding of the deep learning methods that are employed. It will superficially talk about some of these things, but the onus is on you to really research these models themselves. What I'm focused on is sort of demonstrating what's possible, demonstrating a particular workflow with a model that I find to be quite generic, and then hopefully what you get out of this is a means to sort of take these workflows and adapt them for your own particular purposes in your own. All right, I don't see any more people in the waiting room, so I'm going to go ahead and that. So here we are. If anyone does have a question at any point, then please, I would love to hear your voice. I really. So this is the general thing. What we're going to do, we're going to import our libraries that we need. We're going to use the Error-scapes data set. We're going to have a look at that data in a few different ways. We're going to plot those data, and we're going to set up a model to essentially find all of the pixels in the image that are associated with vegetation, which is just one class in our multi-class data set. And then at the end, we're going to transfer we're going to transfer that model essentially to a different data set, and then we're going to start learning on that second data set and see how and see sort of just demonstrate how transfer learning could be an extremely useful thing for you. All right, so here we go. Hopefully you're following along here. As I say, feel free to ask questions. I'm also going to stop at points along the way here, especially during model training and things like that, and open the floor up for discussion. But for now, I'm going to go ahead and run this first cell. So to run a cell, you're sort of hitting Shift and Enter, or and if you just keep hitting Shift and Enter, it will automatically go to the next cell. This is a piece of code that's just for the purposes of seeing how much what hardware you have. The notebook is actually set up in such a way that the GPU is already loaded, or it should be. If you go into runtime and then manage session, runtime and then change runtime type, you'll see what we have here. This menu here is we've got the GPU selected because we're actually going to be training a model on a GPU that's hosted on the cloud computer. We could also use a TPU for this. If we selected none, that would mean that all of the processing is happening on CPU, and that's going to take an order of magnitude time. Most of you, I imagine, have the sort of the standard Google Colab account. I actually have a Pro account, and so that's why I get an option here of a different runtime. But you should just see a standard there, and so that's what you should have. So it's a Unix-based computer that's actually running this stuff behind the scenes, and so we have access to a few Unix-style commands like NVIDIA SMI, which tells us what GPU we have. I have a Tesla P100. You probably have something a little smaller, and it tells you how much RAM we have. I've got 13.7 gigabytes of RAM. I don't know how much, but whatever you have should be sufficient. Okay, so this next part here, the Error-scapes data is actually available. It has its own GitHub page that I've linked to here, and they actually make their data available via a Google Drive link. So this little bit of code up here is not too important. It just allows us essentially to download a file from a Google Drive. It specifically extracts a particular string out. It uses a particular string that's in the URL of the Google Drive link, and it just uses that to download the data. Okay, so it's not too important about that function there. What's more important is what the data is. So the data set consists of 3,269 images. There's 720 by 720 by 3. That's actually fairly small for a UAV image. You're probably working with images that are larger. The semantic drone data that we're going to look at later on, they're a larger format image. They're probably 12, 14 megapixels, something like that. The classes that we have, these are generic classes. I didn't want to get too specific for the purposes of this workshop because you're obviously coming at this from different places. So I chose a data set that had these sort of a mixture of natural and unnatural classes. For the most part, the scenes are natural. They're sort of mostly vegetation and background, essentially. Background is, I guess, everything that's not that's not anthropogenic or vegetation. Okay. And then obviously there's a lot of sky, and then there's a lot of other sort of anthropocentric class like animals road. So we're just downloading this file here, and then that shouldn't take too long. And then we're just using a couple of these Unix style commands to interrogate our data. That first one, tar, that's just for taking a tarball, which is that tar.gz, you compress tarball, and extracting that just in much the same way as you would extract a zip file. And then ls, it's just for listing what's in the file system, and I'm piping that to another command here, word count line. So it just essentially just tells me how many images I have. And so my imagery, my red, green, blue photographs, they're contained in my Aeroscapes JPEGs images. And if we go over to this tab over here, hopefully you can see my mouse. If we go over to this tab here, you'll see our files. You may need to hit refresh. You can go to Aeroscapes and you can actually see what subfolders are. We're just going to be using JPEG images. You can even, if you're not familiar with Colab, you can actually even, there's a lot of images in here, so it might take a while, but once this goes, you can actually double click on an individual image and just have a look. Now this is a label image, and so you look complete black because the labels are encoded as integers, and we only have something like 20 classes, so there's numbers in there that are sort of distributed between 1 and 20. But most image viewers are expecting an 8-bit image, so it's expecting your image values to be distributed between 0 and 255, which is why you can barely see it. You can actually just about see it if you really squint. But obviously, if you look at the actual images, they'll look like actual images with their full dynamic range, like so. So you can sort of tell like the sorts of imagery that we're working with here. It is a landscape in some respects. It may not be a landscape from any particular technical definition, but we are sort of looking at landscape and landscape. All right. So back down to here. I imagine you might be at a different stage to me, but I'm going to just keep working through this in this way. This is just a piece of code that's going to give me a list of those images. All right, so I've just made a list. I've just used the glob, which is a function for essentially pattern recognition, looking at strings and seeing which fits a particular pattern. The pattern I'm imposing here is anything that's got JPEG extension for an image and anything that's got PNG extension. And then I'm using, and that comes out as a list, a Python list, so I can use sorted to then sort those. And that's going to be important to sort them because later on we're actually going to use these two lists and pair them together. Okay, I like to use color maps that mean something to me. Color map, if we just sort of go down here, that's what I mean by color map. I've got my background image that's sort of grayed out, and then I've got a semi-transparent overlay on top of that, which is color-coded every pixel in class. And I like to use colors that mean something to me. So for example, I've got this light blue for sky, and I've got green for vegetation, I've got gray for road. In order to do that, I tend to use this command called list color map, and I'll just take a list of labels and a list of associated colors, and it will just take those colors and make me a color map that I can then use within my matplotlib command, such as my color bar, my show command. Some of these, you'll see that I deliberately used a mixture of sort of inbuilt colors, which are listed here. They're red, green, black, cyan, blue, magenta, and yellow. It's similar to MATLAB in those colors, but you can also give it HTML colors as well. And I provided a link here. There's several places that might have colors. So I'll go ahead and load these in. And what it's doing here is just showing you, it's just sort of recreating this image here. I've just chosen this particular image 1000, because it had a few of the classes and it was showing interesting. But feel free to actually change that number and explore a few other. Here I'm just this is a raw. Here is my image, and label is my label, and I just got kicked off by runtime. Odd. That's guess one downside of using Google Colab is that we can't queue up at time. So anyway, what I'm showing you here is the image that I'm using a grayscale color map just to make that gray, and then I'm using my own color map that I defined up here, and I'm using an alpha 0.5, which says plot this with a 50% transparency, and then I have to give it my minimums and maximums here, because not all classes may be represented in every image, but I want to ensure that every color scale is scaled the same way, so my color bar and my colors show as they should. And so what I've done here is I've just done exactly the same, but this time I put it inside a for loop, and I'm just giving it a few different indices of images within my set. So instead of using image 1000 like in the above, I'm cycling through this, and I'm using cool. My runtime got disconnected. So this is why, but it's great for the purpose. Right. So here I'm just unpacking. I'm untarring this again. It doesn't actually matter for the tar command. It's just going to overwrite everything. If you're using a zip command here, it's prompt you say overwrite. But because we have it tarballed, it doesn't matter. And I'm only going through this again because I got disconnected from my runtime. If you're any doubt what that means, then you should consult the up in this corner. It should tell you if you're connected or not. All right. Hopefully I don't get disconnected again. So here it's just cycling through a bunch of different images, and it's making a plot. And there's a few different images that I sort of cherry picked because they show different things. This is an image where it's just a drone over the sea, and there's no sea category, so that goes into background or other. You see a lot of a lot of things like this, where multi-class segmentation problems are actually very difficult to label by hand if you're trying to classify every single thing. So often, if your classification scheme doesn't have the thing that you're looking at, it will go into a separate class called background or other. I'll talk a little bit about that, what I think about the practice a bit about that tomorrow. But you can see, for the most part, you can see that the scene is not other, it's something. We've got large areas of sky, we've got large areas of vegetation, big swathes of road, and then other little bits and pieces. Construction here means building. Obstacle, it's difficult to tell really what that means. That's another class in this particular data set, which is a little bit ambiguous. So for example, this is an obstacle, it's a door that's going into somebody's backyard. But if you look at these data more closely, you'll get a sense of how many of these classes are represented in the data set. And I can tell you that, for example, boats and drones and cars and bikes and people, they're relatively rare in this data set compared to sky, road, vegetation, structure. So it's really those classes that we're going to be focused on as we go through this workflow. Okay, so now we have the data set loaded. In this particular case, we had a Google Drive link and we had that data all available to us. You might have to get your data into some particular into a way that is amenable to these algorithms. And I'll talk a little bit while the model's training later on. I'll talk a little bit about the size of imagery and how that relates to the size of feature. And if I don't talk enough about that, then please chime in. Okay, so for the purposes of this lesson here, we're going to be just focusing on vegetation. But this is an opportunity for you to sort of you could change this vegetation with any of the classes that you might be more interested in, and you might want to play around with some of these classes. I've specifically chosen vegetation as the class of interest for this particular clinic because this is a clinic that's been attended by ecologists, and so obviously vegetation is pretty generic ecological class, but you might be more interested in other things. So I would, I strongly encourage you to play around with these workflows for the classes, and you'll definitely see a different response to how. The second reason why I used vegetation in particular is because vegetation classes are also represented in my other data set, a drone data set that we're going to do. So I wanted to make sure that I'm choosing one class that is. And what this piece of code here is really, it's just finding the number that's associated with that class. So these classes are arranged in a list of strings, and each string is the individual class, but they're also ordered in a specific way. And when the model is trying to use that class, the model is using a representation of that class, which is an integer. So all of our labels are images that are composed of integers, and in our particular case, all of the number 9 in our data set, they all refer to pixel and so okay, this is an important part here. Training neural networks, I know we haven't got to neural networks or training yet, but training neural networks often requires feeding the model images small batch. There's a couple of different reasons why that's done in that way. Partly, most deep learning model training happens on GPUs and not CPUs. And GPUs don't have as much memory as your CPUs have. Your RAM is typically much larger than any of your solid state memory. The reason why GPUs are used is because they have many more cores, and so you can distribute training much more computationally. And what that really translates to is model training times that are if you were to train this particular model on a CPU, it might take days, but on a GPU, it takes minutes to hours, and that's different. But a big downside with using GPUs is that you're limited by your image sizes and by batch. If you're providing the model large numbers of very large images, you'll very quickly fill up your memory and you'll get a resource error. So you're usually faced with two choices. You either have to make your images much smaller than they really are. I'll talk about why that may not necessarily be a problem in a minute. But oftentimes you also have to make the number of images that are presented small. You can't just feed all of your 2,000, 3,000 to the model in one go, and you probably wouldn't want to anyway. Because another big reason why we're training batches is because it's another good way to regularize our model. It prevents the model from overfitting. If you're feeding the images to the model in batches, it learns from those batches alone. It goes through the process of setting its weights based on those batches. But there might be other things that you do to those batches that help with model regularization as well. For example, you might scale those batches slightly, present those different version batches to the model in order to give it much more variability. So it has to work hard, learn trends from the data, and not just memorize within. So that's essentially why we use batches. I'm going to stop here real quick and see if I have any comments on chat, but feel free to ask any questions if you have them. Actually, I don't see my chat.
Next to participants, lower parts.
Sometimes when you're sharing your screen, you have to press Other on the right side of the bottom of the Zoom bar. That's what you appear.
Not see either of those.
Or click Escape, maybe?
Sorry? Oh, here we go, chat. Okay, doesn't look like anyone's chat chatting. Has anyone put a comment in the chat that they know of?
Yeah,
I think there's some comments in the chat. Mine says, like, what tools do you recommend for labeling images? In the beginning, why test data is blank black?
I'm having a few issues with this. I'm using the Zoom on Linux, and I think that everything's in maybe a slightly different place. Unfortunately, I don't see my chat. So if anyone would like to re-ask that question, that'd be fine. Now would be a good time.
Go ahead, Sarah. You did an awesome job. I think. Can you?
Oh, so these are not my questions, but what it looks like Robert posted. What tools do you recommend for labeling images?
Okay, that's a good question. I currently recommend a website that's called makesense.ai. This is really cool for a couple of different reasons. Partly it's open source. You can actually download this from its GitHub page and run it locally. Or you can run it through the URL that's made available here, but it doesn't store any of your data, which is important for a lot of folks who work. It's just facilitating you to upload your data so you can download your label. And then as soon as your session is over, you can be basically assured that your data is not gone off someplace. So you essentially drop your images in here. I don't know if I have one. Maybe I have one in here somewhere. No, I don't. Sorry, I wasn't prepared for that. You essentially just drop an image in there and you start labeling. I should actually show you. Let me throw one of these Error-scapes one in just to make it relevant to what we're doing here. So I've uploaded an image. I want to create some labels. Let's say I want vegetation. Let's say I want water and sky. Or you can load labels from a file. Here, it's actually saying that it's going to try to actually estimate those things for you. Oftentimes, it doesn't work unless you're working with things that are really specific, like people. So oftentimes, you'll say, I'm going on my own. And then you basically use this tool. If you've got a couple of different ways to interact with this tool. You've got bounding boxes. So bounding boxes are just squares. You've got points. So points are sort of just as they say, they're point. You select your label. You select your label like this. So it just labels those. But what we're talking about is a segmentation. So what you need is polygon. So this polygon class here allow you to essentially segment out your features. You can sort of do this fairly efficiently. I'm using a terrible mouse for this and also don't have time. So let's say that you would say vegetation, and then once you've done that for a whole bunch of images, you can go to export as a VGG. So that's a good one. I would recommend that for generating your data. Does that answer the question?
Yeah, thank you very much.
Okay. All right. So assuming then more people have questions, apologies for this chat thing. I did see it when I wasn't sharing my screen, and then as soon as I shared my screen, the chat went away. Okay.
Dan,
yeah.
If you go up to the top of your screen and where it says you're sharing your screen, move the mouse up above that, and all the options should come down from Zoom. And then there's the chat is in the 3 dots to the right.
Oh, thank you so much. Okay, that's awesome.
And then that'll open chat.
All right. Thanks, Chad. Yep. Appreciate that so much.
No problem.
Okay. Yes, the class is being recorded. Thank you for the website. We've looked at labeling. There's lots of labeling tools out there. A quick Google search would give you an alternative. I've researched a few of them, and makesense.ai is the one that I like. So I'm going to just type that into the chat so everyone has. Yep, segmentation needs polygons. You can do that with make.ai. All right. So keep the chat coming, and I'll come back to your questions in a few minutes. So this is go back to the batches. So this is a custom batch generator. Keras has its own ways to generate batches, a number of different ways. But this is one I like because it's sort of intuitive. You can sort of see what's doing a hood. But also, there might be many ways in which you might need to do things to your imagery, such as what we're doing here. You might need to, for example, pair up images in this sort of way, where I've just taken my file, which is inherited from this loop here, which is just one of these files here that's randomly sort of selected from my catalog. That then goes into this for loop, and that's what F is. It's just a string of one file. So it's very convenient for this particular data set. If you want to just sort of find the label that's associated with their image, then really it's a question of finding the file and just sort of replacing it. In this case, very convenient to just replace that file name with a different extension, a default, because the images are arranged in such a way that they're just numbers, and so 0001.png is the label of 001. So it allows you to do things like that. It also allows you to apologies, that keeps jumping every time I in the file. So it also allows me in this specific case to say, okay, this is a label that contains the labels from all of my class, but I'm only interested in vegetation. So we generated that number 9 earlier on specifically for the purposes of giving it the function. So we could say, okay, we can read in our mask, which is our label, but in the end, our mask is really only they pick that number, and everything else we're going to. So this mask is that binary mask consisting of 2 numbers, 0 and 1, 0 for all of the background class and 1 vegetation. And so that's why way I've set up. But I think you'll also find, I think for a generic workflow, it's useful to expose the type of thing. We don't see much in a lot of online workflows. They tend to go straight at which don't work. Okay, so that's what that function does. And so now we're going to use it. We're going to use relatively small batches. We're going to use a batch size of 8. So that means we're going to present to the model during every training epoch, we're going to give it 8 images and 8 associated labels. The size of the imagery we're going to use is going to be smaller than the original imagery. 720 by 720, I think was what the original size was. I've just made that slightly smaller so it fits on the GPU memory, but you could use the original size we had in the image. I think for the purposes of this, we'll run with the slightly smaller size. The other reason why I've used the smaller size is because that's sort of typical. That's more typical, I guess, than not for a lot of data using. Even though you tend to go out and spend a lot of effort in creating very, very high resolution imagery, because you might be sort of maybe piping that to other workflows such as grammetry or whatever requires a lot of resolution. Typically with neural network training, you're actually making degraded copies of your images and feeding them to the degraded in our case because we're making the spatial resolution slightly more. But then the image obviously undergoes a lot of random transformation. We'll see that image is essentially treated. It's squished and it's squashed and its features are extracted from it, and there's not a lot of preservation of spatial of any type of spatial relations. But there's specific ways in which convolutional neural networks do to keep track of spatial. Talk about that. But in general, you're giving it square images. Most models that you'll see out there take square images and not rectangular. Obviously, most images are rectangular, so you're not preserving the aspect ratio of a pixel. But in the end, it probably does that. What we're hoping here is that the model is able to extract features that relate to vegetation, and vegetation, as we all probably all know, is somewhat self-similar. It's sort of kind of flat structure. You have a lot of repeating patterns, a lot of image stationarity vegetation. So for this particular class, it's not going to matter a hell of a lot if we make the images a bit smaller, or even if we squash the shape, change the shape of those pixels, because of the specific way in which the image is going to extract those features. But it is possible that you may encounter other situations do need an aspect ratio. But I would probably suggest it's a relative. Okay, so we're using this function now. We've just called that function. This is a generator function, which is a very specific Python construct that allows you to sort of query the function on the fly. Most functions are sort of x equals function y, and x is returned as a function of y. It's all done at one time. TensorFlow is sort of set up in such a way that all of the computations are done only when they're needed, and that's sort of the whole point of TensorFlow and why it's so useful, so computationally efficient. But then also, generators, they work along the same principle. Generators are used a lot within machine learning or memory limitation. You just want to provide the next batch of images to the algorithm when it's needed by them. And so internally, what the model is doing every time it goes into it searches for a batch of images is just calling a next on a generator. And so next is the sister of yield. So we go back to our generator. Any function that you see that end yield, the generator function, that's interrogating a next. So we use next to get the next batch of images. And so that will be, if we expand this a bit, the length of x will be 8 and the length of y will be 8, because 8 is what we asked. Okay, so if we plot those, this time I'm just plotting just the image in the background and then the generated label. So it's sort of working in a similar way. I'm going through a number of these images and I'm just taking that label, and what I'm doing is just color coding all of the ones in the label by green, and then all of the zeros, they become white. So very quickly you can see that working because the green pixels are overlaying what you write how you use vegetation. Okay, so we're building the model now. We're getting to the point where we're importing TensorFlow layers. We're at the point where we can build the model because we have this generate function. We have all of our ready to go. This is the format essentially that we're feeding the model. We're just giving it these batches of this. These model layers I'm going to talk about a little bit during the model training because the model training takes a few minutes. So I'll come back to the few, but you'll see that the things it's all organized as callbacks layers on. They're your three major Keras workflow components. And at this juncture, I just remembered that I hadn't actually mentioned Keras yet. So TensorFlow is our library that we're essentially using to do the heavy lifting on our deep model. Our deep learning model. That is essentially C++ code that's very highly optimized for distributed compute, sending graphs off to different parts of your computer hardware and telling that and the graph tells that piece of hardware what to do different instant time and what to return. And so it's a very efficient way to do distributing because things happen. Keras is a higher level wrapper to the TensorFlow API that is able to make it a lot easier to use TensorFlow API functionality. Keras is also really cool because it interfaces with a number of other different deep learning, low-level deep learning sort of libraries out there. You may have heard of Theano and you may have heard of the Microsoft one, but it interfaces interfaces. It doesn't interface. It doesn't currently interface with another deep learning framework that you may have heard of out there called PyTorch. PyTorch is very powerful and very cool, but we're not using it for the purposes of this tour. TensorFlow is more common within industry, and it's more common in general. PyTorch is generally more common among computer science research, people actively engaged in machine research. That's not to say that it's not incredibly powerful and useful for everyone else, but you just have it because Keras doesn't, because Keras essentially is pretty good to use, and TensorFlow sort of comes with. So that's sort of workflow that I brushed over this little part here about actually making the model, and I did that for a reason. All of these commands essentially are all of these commands here are just subfunctions that are called on by the main command. This is a model that is not my own original design, but I have sort of heavily modified it for purposes of this for this particular workflow. Just a couple of modifications I made about that. But this is the entire block of code that your big model. That's pretty cool that static set, even though it may look like complicated code, it's really not that bad, especially considering the complexity. Okay, so this is where I want to talk a little bit about class imbalance. But before I go there, anyone has any questions while I solve? Okay, so one question from Julia. Oh no, I'm Kerry. Kerry says, how many images do you need to label before you start? It's a really good question that doesn't have an answer, and I think we'll revisit that maybe later on. The short answer is it really depends on your data, and it depends on the so I'll talk about that question from the perspective of this particular data set, and I'll also talk about the other data set. And again, I'm going to talk about tomorrow. So hopefully you get enough pointers about that particular topic as I go. Please ask me more specific questions. Do you need to label background or just the class of interest? If you're using MakeSense.ai, you can just label the class of interest because everything else will be background. Background can be dangerous territory though if that background class has something very, very similar to the thing you are interested in. Is there a way to partition the class balance? Yes, class balance, that's what I'm about to talk about right now. And then do images have to be fully classified wall? Not necessarily. I'm gonna introduce you a workflow tomorrow that might help that. Wall to wall, I think what you mean by that is, do you need to label the entire image? And the answer is not, because anything you don't label into a background class. David says, guessing this is model endemic, better to have more images labeled or fewer images more precisely. Again, that's a pretty difficult, yes, I see the motivation behind that question, but it's a pretty difficult question to answer generically to validate. My experience that if you have precise label, then you know that your error is due to your model, not precise labeling. But I've also got a way to refine my labels based on other workflows. Is it easy to extend to multispectral images? Absolutely. Yes, maybe we'll get to that tomorrow. So the reason why it's extensible is because we've essentially written the code ourselves, and so we can add functionality to that code in order to make it deal with that extra dimension or multiple dimensions. It's not particularly common among, especially amongst the computer science type literature that you might be exposed to. The maybe popular science articles or blog posts that deal with how to do image segmentation. They almost always work with RGB images, and they almost always work with sort of existing data sets out there that have been curated for the purposes of method development for sort of application development. So, especially in the terms of natural sciences. So there are relatively few examples of those out there, but I can tell you that they definitely do. There's many remote sensors who are obviously actively engaged in application of learning, and a lot of their data might be geophysical, it might be multispectral or hyperspectral. All right, I'm going to minimize that chat just for a minute, but keep the questions coming. They're great. Hopefully I'm doing an okay job answering them. Some of them are quite difficult to answer because I'm either going to cover it later on, or because I haven't yet exposed you to enough things to really make answer understandable. So I've just asked you to have a little bit of patience, and then I'll come back to cover those questions. But one question was about class imbalance. Yes, that's a big problem. Class imbalance basically means that you have many more examples of one class versus another. In our case, that means that we would almost always have more background pixels. We'd have more zeros in our label image than we have the class of interest, the one. So if you were to look at a histogram of the frequency of zeros and ones, they might, it might actually be like that. You have a lot of zeros, very few ones. That is often a very big problem for algorithms, but it's only a problem because of misspecification loss function. So a loss function is the thing that is actually doing the work in terms of it's the thing that the model is keeping track of in order to adjust its weight to come up with a novel solution. The loss itself is just is a number number that you're essentially trying to minimize. This is an optimization problem. It's a minimization problem. You're trying to find the minimum of function, essentially. And your neural network is the thing that is finding that it's set up to do so because of its architecture rather than any specific optimization scheme. But then there's optimization schemes involved as well. The optimizer, the actual thing that's doing the optimization. We'll talk a bit about that. But what that thing is doing is minimizing a loss. And our loss is the thing that we need to pay most attention to class apps, because the loss function is really the thing that's reporting back to the model about how. And if the loss function is biased towards any particular class, that's I do have, so as I will just sort of footnote that by saying that I've got a larger version of this tutorial that doesn't fit 2 days that I'm going to post online that uses a different data set, and it explores some of this stuff in a bit of detail. It looks at optimizing a particular this model, but optimizing it using different training strategies to come up the best way, and it sort of does that step by step. And I've hopefully put it together in such a way that convinces you that certain loss functions are really bad for class invalid problem, and that other loss functions actually get around them. I'm talking about loss functions here because that is what I'm about to say, but also another way to get around class imbalance is obviously by treating labels. If you're labeling imagery in such a way that the labels, that the classes have about poor representation among data set, then obviously that's not a problem. We're only talking about where there's a huge difference. So one particular function that's really good for these binary segmentations in general is called the dice coefficient. Dice. It's a good way to deal with binary segmentations because that's what I do, but it's also a good way to deal with class. And I'm going to talk a bit more about tomorrow. But for now, we will sort of take it that on an article of faith that this is a good dice loss is good for us. It's very similar to a metric called the Jaccard index, or intersection over union, which looks at the intersection of two polygons and their union, which tells you to what degree they have overlap. The problem with the IOU score is that it tends to result bias towards the class that dominates. So in our case, that would be the background class. So the dice loss is a subtle variation of the IOU score that essentially it weights things the same irrespective, which is what we need. Okay, and this is the IOU score here, and I'm going to define it here just so you can see it, but also we'll keep track of it and compile the model because it used how to. Okay, so we've defined our batch function now. We've got a function that will make our model, and we've defined our loss function. So now we're in the position of actually making the model and then compiling. So compiling doesn't actually mean in the sense of if you were to compile code, you're turning 0 as 1 interpreted by a machine. You're sort of doing that here as well, but the main thing about it is that you have to specify certain things you need to function. You have to give it an optimizer. So the optimizer is the thing that's actually is the algorithm that's essentially minimizing the function, doing stochastic gradient function. It's working out the stochastic gradient. There's a number of different optimizers. Another really good one for these type of calls. So Adam is basically the same as RMS prop, but it has this thing called momentum behind. It's just a numerical construct allow interrogate Porsche parameter effect. But it's not always you see it a lot. The Adam and you see RMS prop, you see them sort of used interchangeably. Often they do different things, but they often result in that result. And here I'm giving my loss function. That's actually my function here. That's not a particular variable that has it's a function. And similarly, this is a function, my dice coefficient function, and my mean function. You can specify as many metrics as you like. The metrics are things that it computes at the end of every training epoch. It's just a way to report back how well the model is doing. Typically, it's using validation set. We haven't got to the test and validation set yet. And the loss is the thing that's actually being used by the model to set weight. It's the thing that defines how the backpropagation will go, how the back so the model can start training. So these metrics don't actually contribute to the model training. They're just things that you're reporting back to see how well you're doing as you go. These models take a very long time to train. So if you're monitoring your metrics as they train, you can actually just stop it if you think that it's not going to work out. You develop it. I'm putting these couple of things in here because they're not necessary to our workflow, but they are kind of useful. This is a way to save your model out as a JSON file. It's a metadata format, a human readable ASCII format, and just see how your model put together. But it also allows you to sort of back all of these things up here are Python objects, so they require a lot of work to sort of pack them out to C. But this model to JSON is a pretty useful thing Parrot has inbuilt. So if you need to give your model to someone else, this function here is of course I haven't actually been running these. I'll run that one and run 2, and you'll see once this compiles over here, you'll see if it does, you'll see. Okay, no, it just done. So you go over here and refresh, you'll see they've got a new file, model.json, have a look at that, and you've got this model.png, which is this thing here that's also been printed to the screen. And what you're looking at here is this is what the model actually looks like. These deep neural networks are just layers and layers and layers and layers and layers of things. The outputs of one layer, the inputs of the next, and on you go. A lot of modern sort of hyper modern neural networks have these different branches, connections. They happen at various scales and there are various reasons. I'm not going to go too much of it, but the idea is that you take your inputs and you treat them one way and you treat them another way, and then you combine combine them together. So you've got one sort of path along this that's extracting one type feature, and then another path that's doing something different, and they get added together, and so forth, so forth. These models are large. They consist of many, many layers. Like I said, all of these connections can be quite confusing. There's a reason why these skip connections are there, and I'll talk about that whilst training. Okay, so this is the point where if you go ahead and just run these cells, this is the point where actually downloading this data that I got up on the web, but this time we're downloading just text files that I've already gone through the process of randomly splitting the data into 3 different subsets. We've got a training set, a validation set, testing set. And the reason why I've put them out on, I export them out file is because I'll read them back in. If we were to use different random subsets, especially because we're training our models over a few of epochs, then we would potentially see different things. So this is just for the purpose of, we're just reading that back in from Mark. And this bit of code here, the details don't matter too much, but essentially it's just opening a file and then just reading them in line. And then this last little bit here is just print screen, different numbers of objects. And you'll see that I've got more training files than I have testing files, validation files. And that's pretty typical. You need to present neural networks with a lot of information, all of them to perform optimally. Going back to the question, the first time I'm going to go back to the question about how much data we need. Well, hundreds, ideally, typically, but not necessarily. And it does depend on your data. This data set here has obviously thousands, couple thousand. That's a pretty good number, but it obviously takes a very long time to manually label that number of images. So you typically start small, you make a model, you see how it well performs, you get a sense for how well it might perform with more data, and then you sort of accord it until a point where you've fed it more data and the model hasn't performed even better, at which point that's the brute force way of knowing that you're done. But there's more sophisticated ways too that we argue about as we go. Okay, so this bit of code here is just commented out because that's just showing you how I made those different subsets. So I took half of the image set, and then I took half of the next set, and then half of the next. So I have 50, 20, 25. And here, this is just a piece of code that I use to write those files out, if you find that useful. All right, so before we go on to training the model, I'll have a quick look here at questions. Will the extensive tutorial be posted online, free to access? Yes, it will when it's finished. Almost finished it. That's my goal for the end of the week. And I'm going to announce it to the same email list as here, and I'll give to sister. Is that diagram for one pass of the training? Yes, that's the model, and the data goes through this model many, many, many times. The number of times is the number of epochs, the training epochs. So if you have 100 epochs, then all of your data will go through this entire model 100 times. It does so in batches. So if you have 1,000 images and your batch size is 10, then obviously you're passing sort of 100 batches through this model on every epoch, and then you're doing that epoch number of times. And we'll see that in action now. Okay, this is another piece that's sort of custom to this particular workflow. This isn't necessarily what you'll always see in tutorials that introduce you to the topic, but again, it's useful to have exposure to some of the relatively rare things, because again, something that you will probably encounter if you're doing this for real on your data. This particular class that I've defined here has a couple of different functions within it. One, all it does really is that here, when at the beginning of every training epoch, it will just initialize a bunch of empty lists and a counter, and then what it does at the end of a training epoch, it will use the current state of the model to predict. So the model, when it comes to this point, is here, and we're using it. It's being actively trained as we speak, but it's an object, a Python object, so you can sort of interrupt its training real quick to make prediction, and we're predicting on one of the validation files. And that reminds me, I didn't actually talk to you about the sets are. So if we go back, we've got these 3 different sets here. The training files, they're the images that are randomly drawn from the catalog that the model is. The validation files, they're the files that are also given to the model to use to predict on. So for example, in that plotting thing that I just showed you there, that's one of the validation files that it's drawing, in that sense. But it's also the set of files that it's using to define these metrics. So we go back up top, we have these 2 metrics. It's going to be using the validation set to define those 2 metrics. And so it's important that we use the validation set, because those are the images that have not been seen by the model. They've been touched by the model in the sense that we're using the prediction, we're using them defined metrics that track off during training, but they're not the things that are actually used by the backpropagation now to set weight. So these metrics here, which is also why I have two of them, because I can have as list as many metrics I like there, just essentially tree, audit. Then finally, that we've got the testing set, which is a set of files that I like to keep aside for the purposes of just the validation set. If your model's good enough, it's generalized, figured out what things look like in general, how to so vegetation, figured out the sort of fuzziness, figured out the fractalness about it, figured out what features it actually extracts. And then on the test set, you're actually seeing it. So in many senses, you see training. You'll see head that sort of change, but specifically here, values given but not used for the purpose of training. And then test file, we're not going to see it. Have done that's changed that way. So this callback function, it's called a callback function, and it's given this sort of piece of code in here, which basically just tells the model that this is a callback function and that we're going to use a callback framework to execute this function. And then what it's doing, and then all of this piece of code here is just updating those things that got allocated start. So we can basically carry all of these variables through self, which is the self of the program. It's a way to move variable internally, and it will take a random dot choice. It takes a random file from our validation set. It opens the file. It resizes it to what we need it to be. It makes a prediction. This expand dims. That's just because it comes in as a matrix, and we need to turn it to a 10 in order to use it. And so that's just, in this case, that's just adding another dimension to it, and then it makes the prediction based on that form of the data, and then in the end it squeezes that data to remove any single. And so if you're a MATLAB coder, you'll understand squeezes already for Pycode. And then this little part here just takes that prediction and turns it into an image that we can then see during model training. It makes a prediction. In this case, anything that greater than 0.5, we're going to call 1. I'll go back to that. Here, I'm turning this into an 8-bit image just by stacking it in 3 dimensions and then timesing that whole thing by 255. And the reason for that is because in the end, I just want to show this combined image, which is going to be the image itself, the mask, and then the image masked by the mask, all in one image that then get plotted during this month. Probably more detail than you needed, but there you go. So we're not going to train this model for very long because obviously we don't have time to sit here and watch it spin, but we are going to train it a little bit. We're just going to do 5 epochs. Here, I'm just making a function that is going to allow me to save the current best state of the model as I go. So this is what's called a checkpoint. I guess called a checkpoint, always go back to it. It's pretty crucial that you do that, that you save your checkpoints as you go, especially if you're working on Google Colab, anything you can get randomly disconnected. Maybe a few of you have. And obviously, if you're running this on a computer, you could run into issues as well. It's just a good idea to keep check of those. But if you say save weights, save best only equals true, it will only save the best weight. That means it will only save the weights out disk again if the model's made an actual improvement based on the validation loss. And that is what I'm telling it here to monitor the validation loss, because it's the validation set that I'm more interested in. These models are extremely good at fitting to the training set. That's not what you're paying attention to necessarily. You're paying attention to how well it does on the data, not FD, so that's a much better indication. So that's what that means. And then I'm just adding that checkpoint object to this plot learning, which is class that I define, and then returning this as the part, which is essentially just the lib. Here, I'm the file path. That's just going to be this is the file path that's the model results or the model weights are going to be saved to. The model itself is the architecture and the weight, and we already have the architecture. We have way to create that, but we don't have a way to wait. So that's what we use. That it's an H5 file, ATFI, sort of similar to good. It's also the format. This is our training generator. So I'm using my image batch generator here to make a generator that's going to interrogate just the training files. Just call those for training. I'm also going to pass my model a validation generator. The class num there is 9. That corresponds to vegetation that we said earlier on. The size is 512 by 512, and the batch size is 8. So as I said earlier on, all of that data is presented to the model at each training, but it does so in steps, and the number of steps is basically just number of files divided by the size of batch. So there'll be 204 training steps. That means there'll be 204 times that the model's fed 8 images labels during every training. And so you can see that we're talking about massive computation here. We're talking about things that really do need to harness better hardware, big GPU, many. This isn't necessarily some laptop, but obviously it is possible, especially for relatively small. All right, so I've already defined the model. I've got everything I need to start training my model. I'll explain what this means later on, but let's go ahead and just get that going because it's 1:25, and there's basically now training on this cloud computer. Hopefully, maybe yours has already finished training. But I'm going to stop here and see if there are any questions before I start backfilling some of the detail that I've skipped over so far. And if anyone has any questions that they'd like to use their voice to communicate, that would be great. I'd also obviously want to know if I'm going too fast or too complicated.
Hi, Dan. This is Chris. In this line where you're generating the test data and the validation data, what keeps you from getting the same data in both sets?
Oh, because they're interrogating two separate lists of files. So this validation files here was given to my validation generator, and then my training files are given to my training generator. And then when I specified the model here, I said, so train generator, that's always going to be what it expects first. That's the data that's going to be trained on. That could also be a list of files. So in this case, if I would copy this and just paste it in here, if you were to sort of do this on an entire data set without using batches, you could just do that. You just give it a entire set, but it's not necessarily the way to do it. And similarly, you could stick that in. You'll see that too in some tutorials. Not every tutorial you'll see use a generator. We tend to use generator to have large data. Okay, so we've got. Oh, good. Glad that you're finding pace. Okay. When you have a class that, like vegetation, that exhibits a fractal nature, how do you go about choosing the resolution to use for training? I guess this all depends on the cause you have and the time, but in general, how would you choose? Yeah. In many respects, like many things, you develop an intuition for what might work and what might not work, just based on what you've seen working, what you haven't seen working. Things like vegetation are just so different from other classes in this particular data set. There's a lot of self-similarity in our imagery in general, but the specific way that vegetation sort of structure, the shadows, the alternation, the spatial scales associated with alternation of bright and the dark, they are very different than others. You can use many other techniques to query your data to see how well different classes might fall out from an unsupervised classification. So, for example, you could use lots of different types of clustering techniques to see how well different classes within your data set do cluster out in space. And you can do that with your training and with your training data set. You do that with your set of images and the set of corresponding labels. It's a different workflow than obviously what I'm presenting here, but that is a good way. But generally, it's a lot of this stuff involves a lot of experimentation. Like, when I approach a particular task, I'll take a model that I think might work okay, but really what I'm doing is playing with my data to see what works best with my data. Like, I will downsize my imagery to a point, and if I think it's too blurry or too fuzzy, then obviously it's no good, and I put that up. Another thing that I didn't mention was that because we had square imagery to work with from the start, so it wasn't too much of a big deal to actually just downsize that. But if you had very large rectangular images, then you're probably better off chopping that image up into smaller square chunks and then doing the labels on those. It's going to be quicker, more efficient label perhaps, but more importantly, it's going to be more amenable to a workflow. Like if you have very poorly resolved data, like land, or not poorly resolved, but relatively poorly resolved, like that, whatever, 20 or 10 meter style footprint, then obviously you don't want to be downsizing your imagery even further. Your model is already downsizing your image probably more than you're comfortable with. So you want to try and keep that input data that is about as close to its native resolution as you can. But going back to sort of the fractal nature of stuff, I just meant that in terms of vegetation because I know that vegetation has a fractal structure. I don't know about the fractal structure of any other class, so I can't. Yeah. So can you speak to the effect of kernel size in the convolution block, bottleneck block, and the res block functions? Yes, I'm about to do that. Does TensorFlow have functions that could the model framework you built be adapted for panoptic segmentation? So to back up, there's many different types of segmentation out there. So there's instance segmentation where you are not only segmenting that class, but also giving them a unique identifier. Panoptic segmentation, I'd have to be reminded of what that is. I've definitely come across that term, but it's escaping me at the moment. So if you can let me know what that is, maybe I can answer that better. But in general, yeah, TensorFlow has functions that can segmentation and instance segmentation. Those models tend to be a lot more complex, so they're not necessarily entry-level models. They might be progressed to you've got a more workflow does work well. And we're jumping to a UNet is a fairly standard sort of way to do things. It's a very big, deep model. It has almost 700,000 parameters or whatever. But in this particular case, there are other models out there that have tens of millions of parameters that are generally more powerful, but not necessarily easier to work. Sounds like okay. So panoptic segmentation, it could be similar to segmentation, but yeah, there would be Keras workflow for that for sure. Zoltan said, if you chopped up large images into small squares, you get edge effects when you predict classes on a large image. Quite possibly, but there would be post-processing workflows that I'm going to show you tomorrow that will explicitly deal with that. So if you can stay tuned tomorrow, we can talk about that then. All right, so going back to, if no one has any other questions, I'll talk a little bit about what this model actually actually doing, what convolutional neural networks really are, and some of these details that I skipped over before. All right, so one more question. What about classifying features from elevation data? Absolutely, that's possible. It works in a similar way. You don't have as much information to work with because you only have one band, but yes, this workflow could be adapted for elevation data. It currently would expect 3 band images, but it doesn't. It would work the same for 2 and 1 band images. The problem with elevation data, of course, is that it doesn't necessarily uniquely describe a class. So you'd have to be very careful about framing the problem, essentially, that you want your high elevation features to be sort of unambiguously high elevation and your low elevation features or class be somewhat unambiguously. And then, of course, you could combine RGB images with elevation data too, to a 4-band image, which might actually be the update I'll do. Okay, so I'm going to minimize the chat just for a minute and then going to go back to explaining what these neural nets are. You can see if we go back to the training here, just to check in on that real briefly, we can see that we're already on the 5th and final training epoch, so that's good. We can see a few outputs. You'll see different images to me because we're using randomization to call these batches. So you won't see the same images to me, that's not a problem. But hopefully you should see that in general, you can see that some of the vegetation is actually in an outlier consistent way. We wouldn't expect the model to perform actually that well over 5 training epochs, but we'll see in this case actually does that. We'll come back to that. But what it's doing right now is essentially solving a giant numerical problem where you essentially put your inputs on one side of the problem and your outputs on the other side. And this is just an architecture that's been carefully constructed to extract the feature in such a way that it should generate. That convolutional neural networks in general are used for image classification. They do 2 things really well. They take advantage of multi-dimensionality. So going back to a couple of questions about using other type data, other type raster data. Yeah, these convolutional neural networks deal really well with that because they take advantage of low spatial. The big sticking point with neural networks for the longest time in the 80s, 90s, and early 2000s was that the main layer, the hidden layer, the dense layer, is a very, very inefficient way to solve the problem because it connects all of your data on each node to a dense layer, and so you have millions of connections between your data first hidden layer, but none of those connections have any spatial. So what the big breakthrough with convolutional neural network was that they came up with some way that would be an efficient way to extract features from high dimensional data like image, because you have this concept of a receptive field. So the neuron for every portion of the network is not connected to every other portion, but it is connected to a region, and those regions. So it exploits stationarity within it, which is sort of repeating pattern throughout. Now going back to vegetation, obviously there's all sorts of repeating pattern. Generally, plants are similar and other very distinct. So CNNs are really, really good to take account. So that's essentially why we're using convolutional neural networks. Obviously, many more detailed I could go. But if you follow the intro tutorial that flips up on the product website, then you would have a sense for how inefficient neural networks were because we were trying to classify the tiny image in our model was really giant. But using convolutional neural networks, we've got much bigger images and a much smaller model. So that's sort of demonstrate that. So I'll go on to the UNet itself. I did provide this video as well, which was made by the authors of the original model. The UNet came from a paper that was published in 2015, and it was a biomedical research group, but also folks who are really heavy into image computation. And it's a sort of a brilliant stroke of genius, in my opinion, because it was the first model out there that really did a good job combining features at multiple scale. And that's essentially why the UNet is so popular. If you did a Google search of UNet, I'm sure you would hit millions and millions of sites. The reason why they're so popular, in my opinion, is because they combine spatial scale. So if we go back to this, we've got our input image here, we've got our 3 bands, our RG and B. They get sort of condensed down through pooling and convolution. They get condensed down progressively until you get to this sort of bottleneck feature here. This sort of feature that's only 1024 digits long, sort of numbers long, and that essentially contains all of the information about class, and then it sort of gets upscaled now. Couple of different details here. One is that because the downscaling uses convolution that sort of spatially share weight, you use a concept called transpose convolution to essentially reconstruct how each set of convolutions would then sort of scale up spatially. So it's a little bit more complicated and sophisticated than just simple interpolation like that. It's actually spatially informed interpolation using weights from the convolution. And then these gray arrows, they're actually those points within our model. If we go back to our model back here, just real briefly, and I mentioned these skip connections earlier on, you see that some of these skip connections are really long. Like one, for example, goes all the way down to the bottom, or near to the bottom. And that's because what that that's the intuition behind that is that anything that's going off on this path over here is going to be pushed through all of the different layers. You know, it's going to be progressively downsized, and it's going to have all of its information extracted from it in a very prescribed way. But in the end, it's going to be very sort of low-level features that are encapsulated by that process. Very obvious difference between classes as represented by image feature. But also because that's going to lose a lot of your, even though the convolution is going to be retaining quite a bit of your spatial information, at the same time you are losing some of that spatial information. You're losing some of the very detailed features. And so what this skip connection does is it just sort of adds the output of this, which is still quite large compared to your input imagery, and it just sort of essentially just bypasses it, and in the end it will just add it. It will just combine those together, concatenate those together before it actually makes prediction. And it's designed to preserve both low-level features and high-level, which is also, I think, why it's somewhat useful for the sort of like intermediate scale problem. You know, this sort of size imagery where we're looking at maybe tens to hundreds square. But it also works pretty large imagery. It also works for microscopic imagery, which is what it's designed for. Separate. So that's all I'm going to talk about for the purposes of just moving on here. But I am going to return more. I'm going to return again to what a unit really is and what it's doing for us. But I just wanted to show you the process of actually training this model. We did this over just 5 training epochs. And if you saw some of the scores down here, you'll notice that our dice coefficient, which goes between 0 and 1, pretty high. Our IOU is a little lower, and our validation sets are not too bad. 78. That sort of would roughly translate like 78% accuracy. So, and that's for individual batches. So you can see this, but it's not as good as it might get over many training epochs. And you can see that if you go have a look here, it's quite remarkable actually that the model could figure out really where the vegetation was for the training data set, which is blue line, to an accuracy of about 87% just after the first training, which is amazing. And not typically you'll see things start right at the bottom, they'll get to that point, they may get. But for vegetation and for this particular data, it's a very class. It shows that you can train this model pretty well to train epochs. But you can see that the model hasn't necessarily generalized that well. Still some room for improvement there, because you can see that the training is the sort of score is going up and up. The validation score is bouncing around quite a bit, and it's doing that because it's seeing a new batch every time, and that batch might contain something unusual, not so model. And so really, you'd probably in this case want to train for quite a few more epochs, because you want that validation score to sort of start leveling out. You want two things really. You want consistency in your scores, and of course you want your score to be high first. And over here on this right hand side, I just plotted the mean IOU as a function of dice coefficient. In this example, they track pretty well. The correlated the mean IOU is significantly smaller because it's biased towards that other class. The dice coefficient in this case is a better metric for us because it's going to be enumerating the overlap of our predict class with our ground truth class, but in such a way that it doesn't get biased by the size of that. And everyone's going to get different curves to me because everyone used slightly batches during training. But the expectation is that everyone would sort of converge to the same number after a certain. So here is a convenient way to just quickly test that model. What we're doing here is creating a new generator just from our test files this time. So that's the third set of files that we haven't yet. I'm giving it the same arguments, same size, same class number, same batch size. And it's going to be generating sort of scores. It's going to basically give the model 8 new images at a time, and it's going to just keep doing that until all of the images are used up. And the only reason to use steps in this case would be because this is now a CPU-bound problem. It's using the CPUs using cores to do this. You may run out of RAM. So I'm showing you a workflow here that involves this intermediate steps called steps, and that's for the purpose of feeding that to this portion. And you can see that my test score. This is my average dice coefficient now for the entire test set. It's about almost 8%, which is pretty decent. Our mean IOU of 66 is also pretty decent for IOU score. People tend to say that IOU scores are pretty good if they're more 0.5. But that's not very satisfactory either. So dice loss is a bit better. It's a bit sensitive metric. So here I'm just printing those two numbers out in a formatted way. So I'm saying, okay, my loss here is 0.2. My loss can go down to 0. 0 is what I want. So obviously there's a little bit more room for improvement there that hopefully I get trained more epochs, but already my die score is 8%. And so here I'm using the test generator to just generate a bunch of images. And then here I'm just going to feed each one of those images in the batch to my model, to the predict function here. It's going to generate, and I'm just going to plot. And so this is just a really quick way to see how good the model team doing a more visually intuitive way. You can see, in this case, it's pretty bad. This is the worst one I've seen so far. So this is good. We've got it did really well for this particular image here. Pulled out the individual plots. Did okay for pulling out vegetation this one did all right some of these, but it did pretty badly when it confronted with a picture of water flow. Everything went into the everything else class, and it's picking up. You can see it picking up on the flow from both, and it's picking up surface texture from the waves, which is sort of what it really wants to do, because picking up on similar vegetation. Obviously, in this class, in this case, it needs quite a few more training epics to get to a point where it's not going to use water vegetation. But in general, that's actually pretty decent for a model that just sort of picked and trained for only 5. But just to show you what that could look like, obviously I went ahead and I did this for a few more. And so what this bit of code, you've already seen this function a few different times when we've been downloading data from my Google Drive. This time I'm just pulling in this H5 file that contains weight trained, exactly the same data set, same workflow, same everything, but this time I just trained it for 100 epochs. And then I'm going to actually just load those weights to my model. So destination is, in this case, is this file, and you'll see it's been downloaded over here. It's the one that has vegetation now, not vegetation, and it has 100. So I'm going to load those weights to my model. When you save the weights in that H5 format, it's already structured in such a way that the model knows exactly what to do with those weights. Right? And then this time I'm going to run that same function, same evaluate function that I did before, but this time I'm going to just use using the model that has the new weight load, and hopefully you'll see that the scores are a lot, particularly as you scope significant. And then here, these next two cells are just going to be doing the same thing as I did before. It's going to generating a new batch. Once it's done, it's going to generate a new batch plot. But the one different thing that I've done this time is, of course, this time I want to actually upscale it to its original size. My imagery was 720 by 720. The size of the imagery that I gave the model was 512 by 512. So this time I'm just going to do an interpolation. I'm just going to resize it. I'm going to take the image, resize that, but I'm going to give the image the same size as what it needs, as what it expects, which is 512. So here I've got the image that's been sort of inherited here, and then it's just passing through here. The prediction happens here, and then the resizing happens there, and then just plot. And you can see that it does much better this time. This time we have a picture of open water that's similar to the boat example, but this time it hasn't picked up on those surface textures. It's learned over those 100 epochs, learn how to deal with that situation. I think that is a pretty good place to end. We have 10 minutes left. I do have a whole section on transfer learning though that can wait tomorrow because there's quite a lot of detail there that I don't want to rush through. We have quite a lot of time tomorrow because tomorrow's lesson is loaded. So I just want to end with this recap here, and then I'm going to spend the last 10 minutes asking questions. So just to recap, then we took this data set, we made it a residual UNet model. We didn't get as far as talking about what the residual part means in that, but we talked a bit about the UNet and why it's useful. I would encourage you to play with this a bit, because we're looking at a curated example here for vegetation that worked really well. You can see that it worked with a dice score of 98% accurate. Even its IOU score is 95, which is really, really, really good for this type. And obviously, I think a lot of you would be accept that translated over your prop data. But I would encourage you to play around with this a little bit. Particularly, choose a class that's very small. There's a drone there. There's some objects in here. There's some people. You'll see that the model takes a lot longer to train for these very small objects. Because these very small objects, they're not represented very much in a training catalog as much as they do. We're giving it loads and loads and loads and loads of patient time. But for smaller objects, there may be only a 10% of the imagery has that object. So that's a good case to play with to see sort of how bad you might do for those very rare objects or very rare cases. And it might give you a sense for how to actually label your imagery transfer workflow. In general, these workflows work pretty well for distinct classes, very large classes. The small classes do work too. Not saying that they don't. I've got a couple of different projects where they've worked really well, but I've also had to play around with the training, the loss function, various things to get it to work. Those sorts of topics are sort of touching more upon that second one that second more advanced tutorial that I linked to at the end of the course webpage. That's not quite finished yet. Apologies for that. That will be finished pretty soon. Just give me another couple of days and I'll get that back up. So when that is up, I'll share that around, and you'll see how you might take this workflow and make it a little bit more complicated, or at least adapt it to a more complicated. We've got 8 minutes left. I'm going to go over to the questions and see what we've got. So Danica says, from your diagram, it looks like the final resolution would be coarser than your original resolution. That's right. Yeah, we're using 512 pixel imagery throughout, and that's why we're upscaling it. So it's going to be estimate something the same size as the input that we gave it, but potentially those inputs are smaller than what the original. Is there a way to set a seed? Yes, of course. That's a good point. I don't know if I did that, so that's really well. Yeah. So in here we can use random choice and we can set a seed. We can give it a seed there. So seed is for the random number generator that we're using. And by setting a seed, we're essentially ensuring that we're pulling the same random files as we can. There's a section instruction that shows you how to do that. Can I clarify class versus label? Apologies, I'm using those terms interchangeably. They are the same thing. The class is the thing that you're interested in. The label is the representation that you've made of that class in your image. So I guess they are slightly something. It goes back to that point made earlier on about how detailed do you label it. Ideally, you need to be quite detailed in label because you want to capture just the thing that you're interested in. So I guess that would be where I would make the distinction between class and label. I guess the class is the thing that you're trying to label input. Okay, so I don't see any more questions there. Has anyone got any questions they'd like to use their voices to communicate? So we didn't get it all the way to the bottom, but I think that's not a problem because almost all of you are signed up for both days. And basically tomorrow we're going to start here and we're going to move on to the next part of the workflow. But I want to start here because it demonstrates something that could be useful, and that's transfer learning. So what we did was we create a model for a particular class. And we could actually take those weights and apply them to a different model that we're going to point to a different same class. So you'll see just a sneak peek of tomorrow. We'll see that we're using this thing called the semantic drone data set. I chose this data set specifically because it had vegetation in it too, but it actually has a few different classes of vegetation: trees, grass, vegetation, bald trees. So what we're going to do tomorrow is combine those classes together and see how well our model weights that we transferred from our previous model for the Aeroscape data transferred to our semantic drone data. And by initializing the model with those, we're sort of giving it like a hot start. So if you're a numerical modeler, you might be familiar with the process of hot starting a model. And essentially that's what we're doing here. We're just sort of giving it a bit of a leg up in terms of how it sort of starts to tease out the problem. So by giving it a set of weight that worked well for another data set and then training on top of that, we give it a much better chance to converge more quickly. And that's what I'm going to start with. So go back questions. So would you start building your model with these type of stock classified images? Then potentially that's a good way to do it. So that's sort of what I'm talking about in terms of transfer learning. You could train a model on existing data where the labels are already made for, because the labelings are very time different to, and in fact the most difficult thing about the whole thing in many ways. So yes, I think training, at least developing an understanding of how these things work using other people's data is definitely a good idea before you start to embark on a big labeling exercise, because maybe this particular model is not going to work for you and you won't discover that until too late. But also, if you do decide to use this particular model or any type of model, yes, transfer learning is your friend. Take the weight from that same class or similar class that's been sort of maybe learned over a bigger data set, or many more training epochs or whatever, and then transfer it over. So yeah, if you don't have many thousands of images, of course, that's obviously where you have to start. You have to start with some form of transfer learning, I think, to get you to some point. And the great thing about it is that, you'll see in the workflow that we go through tomorrow, you'll see how well that it does transfer to a completely different data set with different vantage, different altitude, different number of pixels, different spatial resolution. Everything's different. The only thing that's the same really is that it's an RGB image and it has vegetation in it. And hopefully I'll demonstrate. So this is the last question I'm going to answer because we're going to stop in 2 minutes. So if you want to look at image classification of Landsat images, would a CNN be a better option than what we did today? And how different is that to set up? We didn't, that is what we use today. We did use a CNN. A UNet is just a type of CNN. So CNN is a convolutional neural network, which is a specific type of deep learning algorithm that is useful, particularly for image classification. The UNet that we used is a type of CNN. And the specific type of UNet that we used, that we didn't really get into too much of the details, is a type of CNN. So this same workflow would translate over to Landsat images. Whether or not it would be as effective, I don't know, and I encourage you to have it. But you would set it up in essentially the same way. The only thing you probably pay attention to would be, choosing a size of image that would work with a model and that fit inside your heart. Okay, so that is 2 hours up. Hi everyone. Thanks for coming again. I'm glad I didn't scare you off yesterday. There was a few questions that came in overnight. Just want to sort of summarize those first and maybe address those first. But actually, before we do that, let's just go a really, really quick overview of what we did yesterday. So, the purpose of this clinic is to introduce you to deep learning workflows for image segmentation. It's a fairly difficult clinic because there's a lot of code, and that unfortunately you're being exposed to probably more code than you would like or that you're used to at this point, especially if you're starting out Python, especially starting out machine learning. But this is like a real world quote unquote workflow that is sort of typical. Deep learning is still new enough that it doesn't have a lot of canned software that you can just sort of install with. That's becoming a little bit more popular, but for the most part, people are accessing these tools, these algorithms, these ideas by making their own Python scripts, and so it does require a certain Python to do. But with that in mind, there's a lot that you can can. There's a lot that you can do without understanding every part of this code. And I wanted at least to show you a sort of a working example of how you might do land cover, landscape type classification using the sorts of imagery that geomorphologists are now more sort of acquiring, such as from drone, from plane. So that's the sort of scale that I'm sort of addressing here. It doesn't mean that this workflow is not transferable to smaller or larger scales. We talked a little bit about transferability of the technique satellite imagery. Yes, that's possible. There's a few there's a few considerations that you need to take in terms of how you manage data. But in principle, these methods apply to any type of sort of spatial. And the same goes for very small scale imagery as well. I've used these techniques on very close range photographs. They do an awesome job at many tasks they throw at them. But that isn't to say that you don't need to be very careful about what data to give it and how you frame the problem. This is just a tool like any other that you need to understand how to use. So just to recap then of what we did yesterday, we downloaded a publicly available data set called Aeroscapes, which is a set of RGB photographs of various types of landscapes, various places, various types of categories of land cover as part. Those are the categories that we looked at, that's contained in the imagery. The category that we looked at was vegetation, and we just designed a neural network to essentially segment the vegetation picture. We won't do that in class. Today we're going to look at some of those other classes. So we downloaded the data, we made lists, we looked at workflows, plot the imagery with sort of the label sort of semi-transparent over top, and we started to develop an understanding of how to put model workflows like this together, starting with the concept of feeding models batches of images, which is typically how models are trained. And so we first looked at this sort of concept of generating batches of images by making our own generator function with a yield command at the bottom, so we can generate random batches of those imagery and their corresponding masks. We then we just explored that batch generation, then we built a model. We talked a little bit about the UNet model. We hopefully looked at the video that explained it, but we also talked about sort of the basics of what it did and why it works so well. And today I'd like to touch on a few of those topics again, because we didn't fully explain what the residual part of the residual UNet meant. So I'd like to talk a little bit about that. We talked a little bit about class imbalance. Class imbalance is the situation that's very common for landscapes, which is that you have many more pixels of one class compared to another, or of one class compared to many others. So in our case, vegetation it was quite dominant, but it wasn't the most dominant class in our imagery, and lots of imagery only had very small pieces of vegetation, and some of the imagery had a very large patch of vegetation. Generally, it's a class imbalance problem. There are fewer pixels of vegetation compared to others. If you were to look at other classes, and hopefully a few of you did, looking at boats and people and animals and things like that, there is the class imbalance issue is even greater, because those objects tend to be very small compared to the landscape elements. So we looked at this function called we looked into this using a dice coefficient in order to try and get around some of those problems. And I'll talk if you want, I can talk more about that. We made our model. We sort of saved that model to disk, and we had a look at that model in terms of its graph structure. And we talked a little bit about this diagram here. We talked a little bit about these very long skip connections, which are these very long arrows that you can see that sort of connect top of the model, and we sort of covered why those occur or why those are important. Those are essentially how UNets are able to discover low-level features as well as high-level features. It takes the image, it passes it through a series of layers to extract very low-level features, and then what it does in the end is it just sort of merges the feature maps from the low-level features with a set of feature maps that have been inherited from the image without much filtering, and that preserves some of the higher-level features or the finer detail feature within the and that's essentially why UNets are so popular and why they're so useful. We trained the model just for a few number of training epochs with our own custom callback function that we use to plot an example of a validation image as we went. The validation images are those images that are used by the model to evaluate how good it's what you use to evaluate how good the model's doing as it trains. The training data are those images that it uses to actually set the weights within the model to optimize, converge towards a good solution. There's a third set of data that we sort of set aside that we call test set, and that's for testing. It's an independent set of data that's sort of drawn randomly like the other two sets, and it's used to evaluate how good model. We trained the model for 5 epochs, as I said. We stored the weights inside a container, an H5 file format, and format file. We trained the model. and this is a hang up from yesterday's code, and yesterday's lesson. We trained the model, we had a look at it, we found it was pretty good, and we talked a little bit about units. So and we looked at some of the training history. So the training history here, what you're looking at, if you remember, on the left hand side here is the blue dashed line is the training dice coefficient. That takes a value between 0 and 1. The closer to 1 is better. You can sort of think of that as an accuracy score. It's the degree to which the pixels are actually overlapping between prediction and the ground truth mask. And we saw that the validation set was bouncing around. And you would have got different curves. You would have got different curves to me, because we're training on small batches, and they are randomly drawn from a very large training set. So it's very unlikely that we actually trained on the same individual images. And I would say it was impossible that we trained on the same sequence of it. So we're going to have slightly different results. All neural networks train iteratively, and they converge towards a solution over can be a very long time, typically several hours if you're training over tens to hundreds or thousands of training blocks. So which is also probably why when you ran the evaluate command, you probably all got slightly different results, because the model that it's using was trained using it saw different images. So that's a very, very quick overview and recap of yesterday. Today, before I field some questions, today I wanted to move on to a common situation, especially for our scientific field, and that's where you don't have enough imagery to start with. What strategies are available for us to sort of kickstart a model, or to use another data set to examine whether our data set is useful within the model frame. Now, one really cool thing about machine learning is that the practice of taking the outputs from another model and directly using them in your model is totally accepted, and it's encouraged even, because one of the real problems with applying the deep learning algorithms that you can almost never have enough data, and that they are data hungry, and they require a lot of examples to learn from, because the training process essentially. So we are going to move on today and talk a little bit about that in the first sort of hour, and then hopefully in the second hour we're going to move on to the second part, which is contained in the second note. And in that one, we're going to talk about what's called a multi-class problem. And all that means is that instead of just having one class of interest, now we've got many. So we're going to look at vegetation, but we're also going to look at a bunch of other classes and combine them all together in the end. So we have a semantic segmentation, which is a segmentation where every part of the image is something that we can ascribe meaning to. So before I go on to the transfer learning, does anyone have any questions about what we covered yesterday? I do have a couple of things that I'm going to address that I've written down here. I'm going to bring up as I go. One is going to be, how do you take this code and actually use it on your own data? I'm going to talk about I'm going to talk a little bit about the transfer learning. The elevation data that came up, was a couple of questions from folks who wanted to use these techniques with elevation. It's more experimental. There's fewer people who have convincingly demonstrated that elevation is enough to segment landscape in meaningful ways, but that's not to say it's not been done. It is technically possible. You can feed these neural networks raster stacks of anything between 1 and whatever, however many dimensions you have in your data. With elevation data, you typically have just one band, which is elevation, but you might also have derivative products like slope and aspect and things like that you may throw at a problem. Other people have done that within many times within classical machine learning frameworks like random forest and support vector machines and things like that. So I don't think that it would. I think it is worthwhile trying, but I don't have any particular perspectives on it other than it's more experimental. You have to choose your classes correct, because if you're just using elevation data, obviously you have to make sure that your classes zone out by elevation, which is obviously you know that, and it's an obvious point to make. But the more you can do that, obviously the better. If you have two classes that exist in the same elevation zone, then they may be in different spatial locations. So the model has something to work with. The model knows that this particular class is only in in this particular portion of the image. But in general, you probably want some other covariate to sort of use within the model as well as elevation to actually bounce that idea off internally. If that makes sense. So before I move on here, let me have a quick look at the chat, and I'll take any questions you have at this point. I'm going a little bit faster today because I realize we have still quite a couple of people have got errors. I'm not too sure where those errors are occurring. Let me get back to those. Jason says, did your workflow include code to look at the total area of different classes across all the training imagery? No, that's a good point. That's a good thing to do. So what Jason means there, I think that's referring to the class imbalance problem. So one way to actually verify whether you have class imbalance would be obviously to enumerate the number of pixels that you have class. So that would be a simple matter of loading in all of your imagery and just counting the number of pixels that you have in each class, and then perhaps making a histogram or something like that. I could certainly make a note to update that. That would be a simple update that I can make these for this this workflow. So thanks for that. Hopefully that answered the question. But yes, there would be ways that you could examine, the total area covered by every class. Obviously, you need to know what the pixel resolution was, but you could just do it from the purposes of the model training. It doesn't know how big every pixel is. There isn't any way to build that information. There's no easy way to build that information into a model framework like this. So it's not really using that information to sort of to come up with a solution. But that's not to say that that space is not important. As I said yesterday, the convolution filters are set up in such a way that they share weights spatially, and so that's how they're able to upscale the image from the small bottleneck that's created, which is the sort of essential features of the image that are useful for prediction. And if everyone's still with me, then I'll move on to the next thing. These errors, I'm not entirely sure. Chris and Paola, I'm not entirely sure where these errors are coming in. Hopefully I can find them and
don't worry about that now.
Yeah.
It's the first time you train the data, and I just ran the file from the top and got that error. So.
Oh really? Okay. Well, I may have and Paola's fixed hers. Awesome. I may have the same problem, but I'm just trying to figure out where that is exactly. All right. So transfer learning. So this is in this part we're going to take during the training process yesterday we wrote out a file. It had an H5. It's an HDF5 format file, binary format. You can't see it with your eyes, but you can read it into almost any software, and it knows what to do with it. Keras knows what to do with it because the model weights are sort of stored in a very prescribed way. So when it reads those files in, it just literally allocates the weights as it needs to, as it goes to the different models of different weights that are controlling the way the comes. There's also a bunch of biases in there as well, which they go hand in hand. So in general, those are called parameters of the model. The parameters are the things in a deep learning model that the model figures out. Training hyperparameters are the things that we have decided that would include, for our case yesterday, that would be batch size, it would include the image size, it would include the particular optimizer that we use, and metrics that we use like that. But they also would refer to decisions that are made within the model itself, such as how many convolution layers, but in general, hyperparameters are just those things that pertain to a specific model that you can. The parameters are the things that are learned by the model, and those are the things we're transferring over. It only works because all of the hyperparameters stay the same. The batch size is going to be the same. The image size is the same. We're going to use the same models that how. So this is typically how you would start with your own problem. You would take, or I don't know if it's typical, but that's certainly what I would encourage. You would take a similar data set that someone else has maybe looked at or has labels for, and you'd play around with that data set if it seemed like it was going to be pertinent to your particular issue, your particular task. So if you were looking at vegetation in Landsat imagery or whatever, you might take some vegetation classifier that had been made for MODIS or Sentinel or something else, and you just might transfer it over before you start from scratch. If you've got UAV imagery like we have, then obviously, if you wanted to segment out water or a particular plant or a particular feature of interest, there might be already somebody who's done something like that. Or there might be a set of classes out there that are similar for you, that look similar with respect to your spatial resolution. But another way that people tend to do this is actually to just transfer the weights from models that have been trained on imagery that is completely different. Oftentimes you see people sort of transfer weights from what's called ImageNet, which is a very, very large set of 1 million images of everything that you can possibly imagine. It's got thousands of apparently several people were in the sorry about that. I didn't realize a few people were in the wait. And yeah, sorry about that. So a lot of people use weights that have been transferred from this thing called ImageNet. Million images, 1,000 categories. And the intuition behind that is that you transfer weights over from a convolutional neural network that has the ability to recognize stuff images, low-level features, high-level features, and mid-level features that are, sort of generic things that you find in imagery. Corners, lines, intersections of lines, vertices, and things like that, as low-level features. And then that sort of might translate to higher-level features, such as specific textures of a specific spatial structure, or specific spectral structure. So transfer learning is extremely common. We're not going to take the weights that have been learned on a generic set like ImageNet. We're just going to take the weights that we learned that we had our model learn yesterday, and we're going to transfer it to a different data set for this essentially the same classification. The data set we're going to be using is called the semantic drone data set. I did talk a little bit about it yesterday, but just to recap, it's somewhat similar in that it's sort of UAV or drone imagery that's taken from about 10 to 30, I think, meters off the ground. There's more of the there's fewer images, but there's more categories, many more categories, turns out. And the landscape isn't really a natural landscape. It's more of a housing development or something like that. There are natural elements in it, like vegetation, water, and things like that. But for the most part, it's sort of a residential suburb. But we're going to see how well our vegetation works. So hopefully, and of course, because I was talking so much, I didn't actually finish running my own notebook. So maybe I'm going to discover as I do this. Bear with me just a second as I just skip through some of this stuff so I'm able to then take the rest. So essentially what we're going to do, we're going to download the data like we did before. I've hosted it on a Google Drive like I did before. It's a subset of the data, just so you know. The full set of data you can acquire online, much bigger. Both of these data sets I provided link to, so if you were to download them yourself, obviously you could, but they're much bigger in terms of, like, there's a few different but you'll get a say. But otherwise you could just use it. So I'm here. I'm just getting down to the point where you probably have seen it. So yeah, just go straight to. Oh, of course, I'm training my model. Apologies for this. This is unprofessional of me. Let me just go straight down to, I think, where I can revisit this. This is another difficulty with using Google Colab, is obviously you have to sort of run things sequentially, and oftentimes if you miss a cell, you're scratching your head for a few minutes thinking, hold on, what the hell? It worked a minute ago. It's probably because you just didn't run a cell up above. So what I'm doing here is just downloading a zip file that contains the images and a zip file that contains the labels. The images are different in this respect because they're much larger, but we're going to actually use the same size of image, partly because I just wanted to demonstrate that this model can still be effective even if you're radically sort of downsizing your imagery, which some hardware configurations, or most hardware configurations, sort of necessitate. And so what I just did there is just unzip those two folders into a couple of different places. If you use the files tab over on the left hand side of your window, you might need to hit refresh, then you'll see a new folder that's been made called water, and each one of these JPEG images is an image of from the data set, and you can click on one of those. It might take a minute to load, but you can click on these images and it will load them up, and you can see that the imagery is a bit different in terms of its sort of resolution, much higher resolution imagery, and the labels are color labels. They've been made color, so each individual class here has three unique color values that we're going to have to hack. So that's the third type. So I'm just using this. So OS stands for operating system, and walk just means just going to walk through a top level directory, give me everything. So what this piece of code does essentially just cycle through just this folder and gives me the image within it. But if it had been organized with subfolders, it would do essentially the same thing as a part. So because I've got that such a way, I can now just use this type of list comprehension in Python to just go through the images and figure out which ones are the sample images, the color photograph, because those are the ones that have JPEG extension, and the labels, which are those the labels, which are the category which have the PNG. So in this case, it's fairly simple to just break that out. The original data set consists of 400 images, and the reason why this is called quarter is because we're only using 100 of them, and that's just because these are just for the purpose of speed, really. But the original data set has 400. So if you wanted to work with this data, I encourage you to download the image. These are our classes. I've got them in a class dictionary for a specific reason, that will become apparent later on. A dictionary in Python is actually something that, this might be confusing, folks. A dictionary is actually something that's like this. So you might have the value, the name of something, and then you have the value of that something. So your value there would be some variable that's in your Python works. But what I mean here is it's just a class. Let's just call it a class data structure, because it's actually not classically a dictionary, because it's not got this code. And then this is a tuple. Anything in Python that has it's sort of surrounded by these parentheses is a tuple. So basically, this is a list consisting of many tuples, and dictionary was a poor choice word. Here, I'm just extracting only the names because I want to have a variable for later on that just contains the string names. And in a minute, I'm going to extract these RGB color values because I need those values to decode and make a two-dimensional label image out of my three-dimensional label. It's three-dimensional because it has three bands, R, G, and B. And so I want to take those three bands and those many colors, the two colors, basically condense them to a two-dimensional array so we can feed it, or matrix, sorry, so we feed it the neural net. So here I'm prepending this quarter to my file name here because it's not going to know that it's in the quarter directory. And here I'm defining a function that is just going to read an image into memory and a label into memory and resize to the size that we want. We've got rectangular images that are several thousand pixels in each dimension, but the version of the images that we're going to give the model is actually square and 512. We're going to see see that that's not going to be a problem like it sounds. Lots of conventional geospatial work this would be really a bad thing to do. You don't want to downsize your imagery. But for the purposes of the neural network, we have to make sure that all of our data fits onto our GPU memory. And as I said yesterday, our GPU memory is very limited. So unless you have very, very large GPUs or very, very small high-resolution images that you've chopped up, then a common strategy would just be to take your big image and just sort of make it smaller. It's not necessarily ideal, but it does work okay, and hopefully I'll finish that. But an alternative workflow, of course, would be to take these large images and to chop them up into smaller. We did have a question yesterday from Zoltan who asked, whether there would be consistencies between the tiles. So I'll try and remember to get to that. But yes, there should. And I'm going to show you a technique right at the end of today, hopefully if we get there, that will show you how to deal with any type of discontinuities that do exist if you do chop up tree and use a model to predict. So I realize I'm going a little faster than yesterday, but hopefully I'm still making sense. Really, we're just at the point here where we're just defining our own color map based on these RGB values that have been given to us by the people who made the data. We're reading in that array of RGB color values, and we're dividing them by 255 because we want to turn them from an 8-bit integer to a float 0 and 1. Because this particular function from matplotlib, list color map, is expecting the colors to be in RGB but in 0 to 1 format. And here we're making a plot of an example image drawn from the catalog with a semi-transparent label image on top. And you can see that these labels are quite detailed. They've gone in and they've done a very good job being sort of careful about not mislabeling. And so this data is a very good data set to sort of cut your teeth with some of these different algorithms, because it's probably the size of images that you're sort of used to, a sort of a more than 10 megapixel, and it's many classes, which is also probably more like what some of the tasks that you might anticipate needing. But the problem we have with this type of data set right now is that these colors these are colors. They're in RGB color space, and we need to turn them into labels that are just integers that we can feed to our model. The model is not going to understand what to do with a color vector. It just wants an integer to know every class. And so without going into the details, because we don't have the time, this function here really just takes that RGB image and it just looks up what the colors are within that sort of list of colors that I made, and it just assigns an integer to each of the colors in such a way that you have as many integers among the entire label collection as you do labels that you're interested in or that are contained in the data. I will stop in a minute to answer questions, but I just want to get to this point here where I'm essentially first of all, I'm removing the unlabeled category. Unlabeled is difficult to deal with because what does that really mean? Is it unlabeled because they just didn't get around to labeling it, or is it unlabeled because they couldn't fit it into their classification scheme? I imagine it's probably the latter. So it's really unknown, and we don't know what to do with unknown. So for this purposes of this class, I'm just going to get rid of it. We're just not going to use it. For the purposes of what we're doing, we're just trying to see whether we can replicate the type of vegetation segmentation that we achieved the last data set by using those weights. But in the next lesson, we'll revisit this a little bit more in terms of the unknown class and why that's a problem, but also why it's not really a problem, because it really does depend on how you frame it. So this is where we have taken our label image, our RGB label, and we flattened it down to 2 dimensions. So it's now just a single matrix of integers. And here, this is just a handy way to just grab an arbitrary color map, but in discrete form, instead of like we did before, where we sort of defined the color map based on the actual RGB values given to us. And yesterday, when we gave it discrete colors that were sort of intuitive to us, is cyan for sky, green vegetation, things like that. Here, I'm showing you a third way that you may get at this by making a color map, and that's by just using this command, get cmap. And what it does, it just takes any of the existing built-in color maps or color ramps in matplotlib, and will just give you a discrete number of colors, and that's just the length of the number of classes we have. So I've got a new color map here that when I plot this image now, it's going to just give us this semi-transparent mask. No, of course it's not, because I didn't write code. So this time it's going to give us our semi-transparent label, but it's going to be a different color label. And this time the label is just integers. So before I go on to preparing for the model training, does anyone have any questions while I have a look at chat? I realize I'm going a little fast today, but that's only because I do want to try to get to the end. Okay, so there's no new questions on the chat, so I'm going to assume you're okay. But if you did want to unmute yourselves and ask questions, that was all right. So if we go back to our class list up here.
Then 1 second, there is a question.
Oh, okay.
From Parchi. It's in the chat. I can read it out. Okay.
Sure, I've got it. Yeah, so any pre-processing required for shadow? That's a good question. Possibly, yeah. It really does depend on how bad your shadows are. I mean, I would say that the imagery that you see is not the form of the image that is actually used by the prediction. The models are set up in such a way they are quite good at extract features, present significant noise, and even in the presence of significant shadows. But it really does depend, a little bit. It depends on, the sort of the bit depth, color space, and the impression, the various factors that went into making your image. We're not using raw imagery, we're using JPEG or something like that. So there's that, there's that paper too. And obviously the best version of the image that you have to give to the model is the one that you want to use. But also the model is quite good at extracting features. I've worked a lot in Grand Canyon. There's a lot of almost every photograph you ever take anywhere in Grand Canyon has a very dark shadow in it. But even in the presence of a shadow, you can still use these type technique to see what the landscape is posed of. But the short answer is yes, if you can, but only if you know what you're doing. Otherwise, let the mod do it and see how well it works. But obviously, if it's really, really deleterious, then you need to address it. You give it. But good question, thanks. Shadows, things like that, they come up a lot with the types of imagery that we might be using as ecologists and geomorphologists, because we have the vagaries of weather and light to always deal with. A lot of the, that's also a lot of the limitations with some of the materials that you see presented, blog posts and in papers, and especially those categories and models that are trained on sort of anthropocentric classes. You don't have the same sort of issues necessarily with lighting variation like that with landscape. So those sorts of considerations are different. Okay, so if we go back to the list of the classes that are actually contained within this data set, I guess we can just look at the color bar here. You'll see that there's a few different vegetation types. And so, without really going into too many details about what type of vegetation is in there, I thought we would just sort of throw them all in together as one generic vegetation class. But I would encourage you to redo this run through this workflow again with different combinations of those or with different classes. It's only by doing that you're going to get a sense really how powerful this is for this particular problem. But for the purposes of today, we're going to combine the grass, the trees, and the vegetation class. And the other reason why I wanted to show that, because that's also a fairly common workflow that you may encounter, where the model that you want to transfer weights from to your data, they may not have exactly the same classes as I said, but they may have something similar. You might combine them or separate them in a way that suits you. So here I've just made a list of these class foregrounds, I'm calling them, the classes that we're interested in: vegetation, tree, grass. But obviously that could just be any number of those classes. You could just give it one class if you wanted, but I'm going to give it 3. And then this next little bit, that just goes through, and it's just a piece of code that will just extract where that class is found within a list of classes, text, just any class, and it will just append them to this n. And so n in the end is just a list of 3 nums. Those classes as they represent set labels and then numeric that. So we're going to basically tell the model to treat as vegetation any pixel within our label image that is either a 3, an 8, or a 9. And we're going to call them all one thing, vegetation. Here we're using basically the same batch generator that we used yesterday, but this time we've modified it a little bit because specifically because we've got slightly different way in which our data is organized. If you recall yesterday, our Aeroscape data was contained in these 2 folders, JPEG and segmentation class. So we had a little lining there that said grab an image and sort of replace that. This time we've got everything just in one folder. So we're just basically telling it just grab an image and replace things with different extensions, because you'll see that the images and the corresponding label are identical sets. So that's actually the intention. And then the next thing it does, it just cycles through each of our classes in N and just appends them to a single binary mask, essentially. So what we get in the end is a binary mask where the ones in the image are associated with any one of those 3, all of those 3 vegetations, and then the zeros are everything else. So it essentially functions in exactly the same way as the previous batch generator. And so here I just generated a set of images using the same batch size as yesterday, which was 8, I believe. And so X and Y are X's are the images, Y's are labels. And so the length of those 2 should be 8. But the size of any one of those will be 512 by 512 by 3 if it's an image, and 512 by 512, caps lock, 512 by 512 if it's a label. But it actually appends this extra 1 to the image as well, because the model is expecting that, and that appears in this expand dims, expand dimensions there. And I'm saying expand my 3rd dimension. The 0th dimension here is just the sequence of where the image is in the batch. So if I were to treat this like that, then I've got my individual, my 1st or 0th label and my 1st or 0th image. And this little bit of code is just telling me, well, which one of those images contains my class. And it turns out that in particular one that I ran, you're going to get something slightly different because this is randomized. But the one that I ran told me that each one of my images in my batch had that class in. And I can verify that by obviously plotting them. And this also gives a sense of what data looks like. You can see that because this is randomized, it's actually grabbed the same image a couple of times, which is interesting. Never seen that before. But it's also because the image set that we have is a lot smaller. We're only working with 100 images now. Yes, they were. Okay, just quickly consult the chat. Kerry says, can you give an ecology geomorphology example? Is training a new model to distinguish between plant species feasible? Oh, that's a really specific question. That's part of my own research. I don't know yet. I think is the honest answer to that question. Whether or not these...
I didn't mean to derail you. I just was wondering when you're training images through a pavement, if it can move beyond that.
Yes,
but
it can.
If it's too long of a question, I won't derail.
Yes, I would say I'm confident that yes, it can. But it does depend on how you frame the problem and how much data you have. I think from what I've seen so far is that these residual UNet models are very powerful discriminators of objects that are very obvious to your own eyes. At the end here, I'm going to show you, I developed another class that's sort of a more advanced version of this class that actually does go through a really specific ecology example using this exact same model to identify intertidal oyster reefs. And I'll show you that at the end if you want to take that further. And that's sort of an example. It's the best example that I have for how well this model might work on a noisy, difficult data set that may be more what you're used to if you're a remote sensor working in ecology, because obviously some of the signals that you're looking for are pretty small. That's not gonna. I'm not gonna extend my confidence to saying that it's going to be able to identify individual species, because A, I really don't. It's not my area, and B, it's entirely possible that there's not enough distinguishing color textures at every part of their growth cycle or whatever that would give you that reliability. But I would encourage you to just look into it for sure. So here I've like I did yesterday, in order to try to get us looking at roughly the same thing, even though we're training on random batches, we're going to be using at least the same starting point, the same set of training files, testing file, and validation. And they have been allocated by myself, but randomly using this code commented out. And again, like I did yesterday, it's a 50-25 split. I want more training data than I validation. But that's not to say that that's always going to be the case. You may find that giving it a different split is going to be better. Obviously, you want to try and, the most ideal situation is that you're giving the model relatively few training examples, and you're reserving the majority of your data testing, because that's a more that replicated application will have a lot of unique. But in this case, I'm using about double my training file. That's also fairly common. If you don't know what number to use, then I'd say use twice as many training files as you have validation. And if you're able, and if you have enough data that you can actually split it, those three different. Just to reiterate from yesterday, the training data you set weight, reset weight, the validation data internally by model to report how add train. But those data aren't used by the set, so they're not actually used in the solution. So they are an independent set among themselves, and they could be used too. But it's even cleaner, I think, to use it, and it's even more convincing to use a third set where the model has never seen it as your testing set, if you're able. So once again, we're going to train this model. So this time we're going to just use 5 epochs again, like we did yesterday, just because we don't have time for more. And I'm going to skip through to actually get it running, because it takes a few minutes, and then I'm going to go back and explain what I just did. Okay, so you'll hopefully recognize this code from above. This time we're giving it a file path with a set of weights that it's going to write to. We're creating a training generator from our set of training files, like we did yesterday, and a validation generator, and we're evaluating how many steps we want that model to pass through during every training epoch, which is simply just the number of the file we have by batch. We want the model to see every image in the catalog during every training epoch, but we don't want them to see them in the same order, which is why we use batch. And we don't want them to see them all at once, which is why we use batch. What we're doing here is we're training a model from scratch. So we're not this is the version that it's our baseline that we're going to compare to later. We're not using transfer learning right now because we haven't loaded the weights to the if we were to load the weights at this point, we would use the same construct as we used yesterday, and we'd give it some file, but we haven't got that to that point yet. What we're doing is training a model that is, I'm calling a cold start, because it doesn't have any it's essentially starting like it's training with random numbers for weights, and it has to figure it out all from scratch how to do it. And you'll see that as it trains, you'll have different images to me, because again, it's randomizing the batches, and it's randomizing which one it's showing in the validation image here. But hopefully you get a sense that it's even from the first training epoch, it's pretty good at finding the vegetation and distinguishing the vegetation from the rest. And vegetation here is obviously a category that I have chosen specifically because it works. work, but I would encourage you to, again, redo this with other candidates to see how this works in general for other candidates. But you can see that it's going through here, got onto its third epoch already, and you can already see that it's doing an okay job at finding vegetation. So our baseline in this case is going to be fairly good already, and what we're going to do in the next couple of examples is we're going to give it a set of weights that we trained the previous model on the previous dataset, the Aeroscapes dataset on vegetation. We're going to use the version of those weights that were the outcome of 5 training epoch, and we're going to call that a warm start. And then at the end, we're going to use a version of that same of those same model weights, but this time from a model that was trained over 100 epochs, and we're going to call that hot start. And we're going to see what the difference is between the cold, the warm, and the hot models as a demonstration of what you might be able to achieve if you use transfer learning. But while these models are training, I thought it would be a good juncture to talk about a little bit more detail about the model that we are using. Just to recap from above, where we had the image of the unit. I realize this is a difficult image if you're not used to looking at them, but essentially on the left hand side you've got your input image, which is your RGB, and that's why it's got 3 bars. Oh well, actually no, in this case I'm not sure what that's representing, but that first bar would be your image that then got sort of went through a convolution block. That's why there'd be sort of several lines stacked vertically here, because it's going from one thing to the next before it goes through a significant pooling event, which is essentially crystallizing or condensing the features that the previous layer has extracted. But the main point really that I want to illustrate here is it's called UNet because it's U-shaped. This first part of the model is called the encoder down to this point here. This point here is called the bottleneck, and then this expanding part here is called the decoder. And so it's a version of an auto encoder decoder network. Auto because it figures it out itself, just like network do, and also because it's encoding itself, and the encoder because it's encoding that image to smaller and smaller and smaller feature representation of those features till it gets a bottleneck feature, and then it uses that feature along with all of the spatial information that it inherited from the progressive downside in a reverse way to essentially interpolate back up again using the spatial that you rigid. The gray lines, to recap, are those skip connections, those long skip connections that essentially merge high-level feature representation with lower-level feature representation to provide a sort of a hybrid of those two features that modern. That's what's called the vanilla version of the UNet. That was the original 2015 paper implementation of the idea. And then what we're using is actually a slightly different version of the model that has what's called residual connection size. And so that's why it's called a residual UNet. And I just wanted to sort of go over that at a high level at least before we sort of moved on here. But I can see that the cold model has now stopped training. So actually what I'm going to do real quick is get the next mod training, because that's going to take another 5 minutes, and that'll give me enough time to explain the residual model. Okay, so if you're still following, then what we're doing here is we're making an entirely new model. So we're just calling this function yet again. We're giving it a new path to store its weight to, same as the previous one, set pen by warm hole. And then what we're doing here, this is the point. This is where the magic happens. This is where the transfer learn have essentially load weight, because we're loading weights to the same model framework, same architecture, same everything, same hyperparameter, but with a different set of weights. And these are the weights that we learned from the Aeroscape adaptation from 5 set. So we initialize mod, we load the weight. Oh, of course, don't have the weight. They were generated by my train above. So if everyone's not following why I just got that error, it's because I didn't run that model training, so I don't have that file. So that was an unanticipated thing on my part. So let me see if I actually do have that file for the purposes of moving on here. Oh, damn it. No, I actually don't have it. So we're going to have to skip that part, unfortunately. But you should have it if you've run the training above. I just don't have time to do it. So I'm going to move. Oh, do I have this one? Yeah, no, I have that one, right? Oh, okay. Something's gone wrong up here because I should have got that file from somewhere. Oh yeah, that's right. Yeah, we loaded it right at the end of the first one. Excuse me, bear with me just 1 second here. I lost my weight. Here we go. There they are. So this was the piece of code that we download. This was the file that was trained by myself over 100 epochs that we're now going to use to hot start our model. Unfortunately, that means we're not going to get to see the warm, but you should still see the warm go through the file. I hope that's clear to everybody. Let me know if that's not. Okay, so we've now initialized and compiled our hot start model, and we're giving it, this is the transfer learning part, giving it those weights, and this time we're going to just train on top of that. Okay, so while that's training, let's go back to this idea idea of residual skip connections. All right, so what we're looking at here is a figure that originally came from a paper by Drosdel et al., which introduced this idea of using residual connections, and it's now turned into sort of an alternative version of the UNet, and it works better for a lot of cases than the original version, which is why we're using it. The idea behind this is that it's the same, essentially the same structure. You see the UNets, you see the dimensions are approximately the same in this version of the figure, and you can see that it has these long-range skip connections that we talked about earlier, but it also has these short-range skip connections, and they're otherwise known as residual connection. And there's a video that we're not going to look at now, but I do encourage you to watch it. It is a technical computer science video essentially, but hopefully it gives you intuition of what this really is. But essentially the idea is that as well, so every time that these convolution blocks, every time the image features get passed into a block, the skip connection will take a version of the feature that comes out of a particular layer, and it will just combine it. It will just sort of add it, concatenate it with sorry, I'm getting lost. It will take that version of the feature map, and it will just skip the next layer and add it to the output of the next feature. So in this case, you have 3 layers. Your image comes into here, goes through these 3, get pushed through a pooling layer into this layer, which is now small, and then it gets pushed into the next layer. But before it does, it gets sort of skipped over, add back. And the intuition behind that is that each layer now sees not only the output of the previous layer, but the output of the previous layer. So it saw the information that the previous layer saw when it tried to adjust, as well as the output of that layer. It wants to know the reason why this allows for faster convergence, deeper models, more powerful models, is because it sees not only the feature representation that the response particular, but also the information that went into that. So it gets to learn what we're using the same version. And I strongly encourage you to watch that video, which probably is a lot more eloquently in that same. So the residual UNet is essentially the version of the UNet that we're using, and that's the one that I found to be more powerful in general for these types of blocking, at least the types of scale. We're on to the training epoch 4 out of 5. Go through. I wanted to just reiterate some of these scores that you'll see, just to sort of recap this day. And we're about an hour into this clinic now. We've got 1 hour left, so we've still got quite a lot to cover. But the numbers that you're looking at here is the first one's the loss. That's the training loss. That's the current state of the model and where it's at in loss. The loss is going to be going down from a large number and converging. And as soon as it gets to 0, it's a perfect. So you don't ever get 0. You get a small number that's close to 0 if you've done. Your dice coefficient, conversely, that's a number that's scaled between 0 and 1. 1, closer to 1 is. But the things, generally, neural networks are very good at fitting data, right? They're universal function approximators. They're very, very prone to overfit to the data. And so a lot of the challenge, a lot of the art and the science that goes behind learning is to regularize model, which means preventing it from overfitting data, learning the general trend, the general pattern on things that never see like. So the numbers that you really do need to pay attention to are the validation losses. There's no point having a model that has a dice coefficient of 99 if its validation coefficient now is 6. That's the number that we're trying to maximize. Really, we're trying to maximize both of them. We're trying to make sure that those two curves over time sort of converge to the same place. They may not get there at the same rate, but ideally they want to get same place, and that's when you know that you have a good model and update. So the model now has stopped. The hot model is now stopped training. So I'm able to make that comparison. But because I didn't have the warm model, I wasn't able to train the warm model right now. I'm just going to go ahead and comment those out. But you should see, if you've gone through this exercise more diligently than I have, then you should see those curves come out. I'm just going to have 2 curves to look at on every plot. You should have 3. So interesting. Every time you get a different result, you can see because you have different training batches and very few training epochs. So everyone will see a slightly different version of the graph. But most people will see in the end the red line has got a larger dice coefficient than the blue on average and a smaller loss. This is actually a pretty interesting case. This is one of those cases where there's not a massive difference between them in the training data set, but there's obviously a huge difference in the validation set. It's pretty interesting that, no, that's right. So the hot model here is better for the validation set than the cold model on average and maximum, minimum, and mean. And the hot model here has a smaller loss, which is what we want, what we expect. What's odd is that the loss is going up, but I think that's just by virtue of the fact that we're just looking at a very small number of training epoch that we expect. And I imagine you're all looking at very different things. in general, I've run through this a few times. In general, the red line is always better than the blue, but whether or not the green line is better than the red line is completely dependent on the specific images that you saw over this training. So don't worry if you see your green line at top, that's fine. It's also an indication, I think, that this particular model for this particular data set and this particular class doesn't need a hell of a lot of transfer learning to occur for it to sort of get a kickstart on what it would otherwise achieve. What I mean by that is, in this case, we trained a model for 5 epochs and we trained a model for 100 epochs, and there wasn't a huge difference in the ability for those two scenarios to create an improved model. They both worked about the same. But what we'd expect in this case is then to just train us for a small number of training epochs on one data set, and then you're ready to start training for real on your data. And so in an ordinary scenario, you would keep that training going for much longer than 5 training epochs. You would probably choose something at another maybe 50 and 100 in order to see how well that might get. And you'll see over time the dice coefficient go up and up and up, and they'll start a top plateau. And then the loss function will do the same. It will hover just above 0 state. If you ever sort of encounter situations where your loss function your loss value just keeps on going up and up, obviously there's something wrong. You need to stop the training and fix the problem. It's not normal for the loss value, right? It should just going down. For the validation set, it may jump around quite significantly, but the general trend over time is that it's going down, and the variance of its jumps is getting smaller and smaller. So before I go on to and I guess for the completeness here, let's get the test scores for each model. This is the same piece of code that we saw earlier on with the other set. It's just calling this image batch generator function one more time to grab a generator to describe a generator function based on these test files, not training or the validation. So we have our 25 test files there, and we're going to evaluate each one of our models, but I'm going to comment out my middle panel here because I don't have that model. And what it's doing is just evaluating how well the model did based on the entire test set. And we should see that the dice coefficients and mean IOU scores for this one are going to be lower than they are. That's the hope rate. That's what you should all see. There's going to be a lot of variation in the values that you see because you trained on different subsets. I keep saying that, but it is important to understand that this is a random, this is a stochastic process that we train models with. We give models random batches of imagery, and we do things to them that does not enforce consistency. But in the end, you should have a model that, if it's trained over a sufficiently long period, you should have a model that does converge towards its ability, and the consistency that you see should increase. And so we have a situation here where we've demonstrated that a model that has been hot started essentially by transferring the weights from another training exercise, that has significantly, it's sort of given us a 10% increase in our dice coefficient straight off the bat. So it's a good starting point for you to do your model training. And you might even get to a situation just in maybe a few more training epochs where that's good enough and that you're done. So this last piece of code here, before I take some more questions and move on to the next tutorial, that's just taking that hot model and just and doing something with it, making prediction. And you can see that that is not perfect, but it does a reasonable job of finding the vegetation. If anything, it's under predicting where the vegetation is, because it hasn't found in these particular examples, it's done a much better job finding the trees than it has the grass. And I offer the reason for that is because we didn't see grass necessarily in our previous data set. Maybe that wasn't the best class to use, but you'll also see that if you train these models for longer, then it will start grass. So the grass is basically not detected yet, but we would expect that the model would learn how to detect grass later on. It learned the trees because the trees have a much more distinctive distribution of sizes compared to lawns, which have a bigger distribution of size, I would imagine. But also the specific structure of the leaf vegetation is very different from the grasses, which are obviously kept very short. So they just have a very different texture, even if they occupy a similar color. So that's the transfer learning sort of in a nutshell for this particular workflow. I wanted to spend a lot of time on it because I do think that this will be a very common situation that you might encounter when transferring ideas to your own data. Another couple of sort of general points that I want to make before I answer questions is that typically you are using this sort of size imagery. This is probably smaller tiles of images than you're used to using, and again, it's because of GPU memory limitation. We use a GPU, not a CPU, because training times are magnitude short. But the downside is obviously we have a lot of memory issues when we're using very large image, and so we typically either chop them up a bit or, as here, downsize. So with that, I'm going to have a quick look at the questions, and if everyone wants to ask me a question, now would be a good time. Per pixel confidence probability scores. All right, that's a good question. The not easily. It's not a trivial thing to look at the per pixel probabilities. All we have is a sort of a pseudo probability that comes out of our classifying. So if I go back to that, if we go all the way back to our model, actually, we'll see in this line of our model, the classifying layer, or what's called classifying head, the model is using an activation function. And so what that does is it gives you a measure of the probability of it being every class, or sorry, of it being that class, because we only have. So that is a value between 0 and 1, but it's not really a probability because it doesn't come from a joint probability distribution. What we have is a conditional probability distribution of the label given the image, but we don't have. So that's the P is Y bar X, but we don't have P is X comma Y, which is the joint distribution of the image features and the labels. And that's not possible because that would have to be specified over the entire data set, whereas we only have matches work that time. But it's also a direct result of the model itself being a discriminant function. It's not a function that can generate probability distribution. It's not capable of specifying or evaluating, solving, or inferring the joint distribution of two. So what we have is essentially a discriminant function with a sigmoid activation function, which does give us a value between 0 and 1, with 0 being there's no chance that it is that thing, and 1 being that it definitely is that thing, and all the numbers in between. So that is also why when it came to, let's scroll down all the way down to our batch function. Oh no, I didn't. Somewhere in here I have this. Yeah, so in here, for example, this is also why we use a threshold of 0.5. So here I've made a note. So we use a sigmoid function, our classifying layer, that are like probability scores, but they're not true probability. If you said that to a statistician, she would say, no, that's not a probability. But a data scientist considers it a probability because it's entirely data, it has no theory behind it. So what we're doing here is, all I'm saying here is I'm going to call it 1 if it's greater than 0.5. So in that case, that's a decision that I made, and there might be more, there might be better ways to arrive at whether or not that you're trying. But I'm going to touch upon this issue again next well. So hopefully, if that was tired, maybe the next time I say it.
Can we, instead of a binary result, actually get that continuous data between 0 and 1 and look at that in a map?
Yeah. So okay, we can do that right now. So if I gave this a color bar, I'm going to make it smaller, and then here I'll just get rid of that line. And I'll run this again, and this time you'll see a color bar next to every subplot, and that's going to show you where you are within that space. The color map I've used here doesn't necessarily give you a good indication of that, so let me use something a little bit better. What would be a good one? That one maybe? This one's going to show reds and blues. So you can see that in this case, it looks like a lot of the values ended up being 1, but there are many values on the edges that would be less than 1. Oh, in this case, actually, you've got more. There's some values that are more than 1, which doesn't seem right, but maybe that's not right. But yeah, that's how you would essentially look at those sigmoid scores. So it's not too much of a leap actually to just always do that threshold, but because a lot of the values end up sort of bunching up in the 0.9s up to 1. But as I say, you would probably figure that aspect out for your own particular problem. It would also change obviously if you had many class, and you could use the relative scores or the overlap scores in different ways, and that's sort of that's a good lead into what we're going to cover next. Does that answer your question?
Yes, thank you so much.
Well, let me just kind of one more look at the chat. Leslie wants to see everyone's models. I'll let you guys confer over that. So, one person got a hot of, I'm not too sure what that means. So did the loss function and metrics you specify influence over under prediction? Jason, could you explain what you mean by that question?
Can you hear me?
Yes.
So you noted in this model that there was some potential under prediction in the vegetation. And I'm curious, if we specified different metrics in the loss function, if use of different metrics might push the model to predict more vegetation, be more aggressive or be less aggressive in how it's classifying things. I was just curious if your specification of the metrics you're using and the loss function you use kind of can influence how the model is predicting.
Yes, it does. And that's a good question. So let me go back to the loss function that we're actually using. The dice loss function in our case is appropriate for the class imbalance issue. But because we're using 3 categories, I think you're right in that perhaps a better way to do this, or a better way to actually tease out whether or not any one of these 3 classes is badly influencing the model, would be to separate them out and give them their own loss functions, or to weight the loss function. So you'll see examples of people using weighted loss functions if they have class imbalance even among the classes that they're looking at. So in this case, we have class imbalance among grass and tree. And I don't know too much about the vegetation, but we certainly have fewer tree pixels than we have grass. So that would be a case of much more advanced case of using your own your custom loss function that would be a modification of an existing loss function that would weight those classes different. That's another way that you can get around class balance. Does that address the question?
Yeah, it helps. Thank you.
Okay. And yes, so there's stochasticity in here. This is why you're seeing different scores. And a couple of people are seeing their cold model better than their hot model, perhaps. That is just a function of us training over very few numbers of training. I would say that if you trained over many, many more, you would always see that hot one better. It's just by virtue of the fact that one batch over these number of training epochs, they could just throw the model into a different trajectory that it takes a while for it to come back. So as you know, a way to visualize what this model is really doing, I find it intuitive and helpful to think of a lost landscape, right? So you have this, and that's what a lot of people call it. You have this landscape that's full of hills and valleys, and one of those valleys contains the optimal solution, right? Your learning rate sort of specifies how far you can jump across that landscape, and you may start, at some point you may be on the top of a hill, which is where you really don't want to be, but you may sort of descend through training. You sort of descend into maybe the first valley, and you have a look around there to see whether the optimal solution is in here, and then you might have to sort of climb back out of that valley into a deeper valley, and it's a deeper valley that's going to find that you're going to find the actual minimum of function. So the stochasticity is because you all start with random numbers when you're cold starting. You're introducing random batches at different times and different chronology for that number, and it takes a long time for the model to figure out it. One of the reasons why we do train these models over typically 100 epochs, is because it takes a long time for the model to figure out that it's in the right valley and that needs to stay in that valley and just figure out where in the valley it'd be fine. So hopefully that analogy is, but that's the reason why you're there. But if you all train that model for 100 and sent me the result, I'd be really excited, because that would be a good way to actually know how. Okay, so I'm going to address. There's one more question here about subdividing the classes, lumping or splitting. I'm going to address that in the next tutorial, just for the purposes of completeness. I would like to move on from this one if anyone doesn't have urgent questions. Hopefully that was convincing that the transfer learning is useful, even though some of you are seeing variation. Okay. Actually, before I move on to this, but just I wanted to remember to say that. So this is going back to this is our course website, the Deep Learning Landscape Classification that you all started from. You probably clicked that link in order to get here. We're now moving on to this one. We're using the same model now, but for a multi-class segmentation problem. So we're going to be sort of estimating a few different features at once. But I wanted to just go to the end here because I did manage to finish this additional course. So this one's a little bit more complicated, but I wanted to just sort of introduce it to those folks who really do want to take this method and try and run with them. This is a more complete course because it shows you how to organize your data, how to generate the labels, and how to deal with different label formats. It's also using a data set. This is not my data set, fully acknowledged here, but we're using a data set that comes from Duke University. It was used to train a model called OysterNet, and it is basically for detecting intertidal oyster. And it's a much more difficult data set. So there's a few different strategies that I've gone through here, but it goes through from scratch, like how to prepare the data, different, getting everything ready, doing augmentations like that. And then it steps through 3 different training strategies, essentially, and converges on a good solution in the end. And so it's a bit more of a complete case study for specifically, remote sensors on the call who are interested in these very sort of difficult problems. It turns out it's quite difficult to segment some of these reefs because the roughnesses are very similar to other roughs in the land. So enough of that, but that's available. It's going to stay up there. You're quite welcome to look at that. And if you had feedback for me, that'd be awesome, because I'm trying to make these tools as accessible as I can. So without much more ado then, so you've got these 2 sites now. So without much more ado, let's move on to the second, the last part. We've only got half an hour left. So this is we may not get to the end, but this is hopefully, or we may get there fast, but hopefully this gives you a few ideas, some codes, and a starting point to, a specific workflow that you might combine some of these models that you trained binary segmentation. To reiterate what I said right at the start of yesterday, I find it valuable to treat segmentation problems with real world data, these messy data that we have. I'm paying too much attention to chat here. Treating this as a series of binary decisions. There's a couple of reasons for that. Partly is because you don't always know what labels you need in order to make the entire segmentation work of your entire landscape for a multi-class problem. If you're just interested in one class, that's one thing. But if you're interested in many classes, what I'm talking about here is a workflow that's going to combine models that were trained individually and then use a secondary workflow to then sort of deal with any mismatches or weirdness that could result there. And this goes as to Zoltan's question about, if you're in a situation where you've got very large imagery, you need to chunk up into smaller tiles. It's conceivable that you could have the model working in prediction mode would segment that entire scene in such a way that one tile and the adjacent tile might have classes that don't overlap at the edge. And so this would be a way, this workflow that I've got in this particular workbook here is this would be a way to deal with that situation in an objective way. But there would be many ways that you could deal with that situation using geospatial tools or some form of logic came up in order to assign those values. If you had a windowing approach, that is a good one. I mean, if you had a very large, let's say you had a satellite image and you windowed it, and then you had predictions for every window, but there was a 50% overlap between the windows. So then you could use like an average or a mode. But this workflow that I'm going to show you right here is a way to deal with that using a more powerful model called a conditional random. Okay, so I'm going to start by what we're going to do here. We're going to load the same libraries and we're going to use the same functions as we did previously. We're going to use the same metrics and the same models. So I've skipped through all of that stuff because you've seen it all before and there's not much about it. So I really want to talk about, we've talked a little bit about hyperparameter as well. So really I'm going to skip here down. We're going to use a batch size of 8 and we're going to use an image size 5. 512 doesn't have to be on the log2 scale. It could be any number. For now, let's just use 5. So we're going to download the Aeroscape data again because we're in a different go through that. We're being back-ended by the kernel user, so we read that. Hopefully that doesn't take too much time. We're using this Aeroscape data, so that's the same data that we used at the start of yesterday. So that we're going back now to our vegetation, sky, road, things like that. This should be familiar to you because it's the same code that we used yesterday in order to ascribe colors to labels. I'm using a combination here of HTML color code and inbuilt color. Doesn't matter. No, and here I'm making my model. I'm using optimizer as yesterday. I'm not this time keeping track of the mean IOU. So that was just the metric that I really care about. And again, this is the files that we're going to use to enforce some level of consistency among our respective output. But that's not to say that we're actually going to get exactly the same. The number of training files again is double the number of test validation files. That's not for any particular reason. It's just a rule of thumb that I have to apply. Okay, so what we're going to do instead of waiting for all of these models trained, I've got all of these models already trained for a subset of the categories. I ended up choosing just the categories that I was really interested in. I'm segmenting the landscape in this sort of pretend example here, so I don't really want to know where boats or where people are. I'm more interested in where the buildings are, what construction is, where the obstacles are, which is just things like fences and posts and stuff like that. I assume it's obstacles because this is for some sort of robotics application, but there's sort of obstacles to some sort of device or vehicle. My background class is sort of my catch-all class that contains lots of landscape elements that don't quite fit into construction, vegetation, road. So all of these files, again, they're all hosted on Google Colab. I've just downloaded them. They're all H5 files that contain model. The model is the same model. I just basically pointed the model to the SIG class and had it go through the protocol. Now, you probably have realized that is not the most computationally efficient way to do. But and of course, there are models out there, including the UNet, that can adapt to multi-class problem. You just set things up the same way, but it takes track of one set difference. But what we're doing is I'm proposing a different way, which is to essentially treat it to exploratory in an exploratory fashion. Look at the class, and we're sort of simulating a situation here where you may have classes, you may have inherited some initial classes, and you want to see how well they work, or you added more, or you may be on the fence about whether or not a certain class might actually work, and you've gone down the road of creating a few of those labels from imagery, and now you're in a position where you're like, okay, I want to see how well this label's going to work, and I'm going to sort of do that for a few. And so what the workflow that I'm showing you here is sort of a very specific one that is not particularly common even, but I think is one that's worth exploring for those reasons. It also allows you to examine the errors in isolation. Oh, and of course I don't have that file. Bear with me just a second here. I don't know why that give me an error now. What this piece of code code is doing. So this is just a very efficient way of loading all of my models in, but really it's just replicating something like model vegetation equals res unit size. This is where I'm adding my third dimension. If I had a single band image, I would just leave that as size, but because I've got multiple bands, I'm just sort of using some tuple math there to add together, and then my batch, right? And then I'm saying, okay, model vegetation, compile, the next line of each one, and then load weights would be the third. And all I'm doing here is making that more efficient in terms of coding, because I have a list of these classes that I'm interested in. So, and because the way that I construct each model is going to be the same, I'm essentially just using the exec command, which is similar to the eval command in MATLAB, but you can just evaluate a statement, which just execute that statement. And so it's a really useful, a little advanced way to sort of make that more efficient. But essentially all it's doing is this, but just doing it. So I just need to spend just a second here trying to figure out why, what's going on. And I imagine everyone else is telling me that file is you read it. I'm seeing that file. Interesting. If anyone wants to chime in here, they could give me a hand. I don't understand. Is anyone else seeing that same thing?
I got the same error, Dan.
Well, I'll be darned.
And I didn't, but I was having problems downloading one of the zip files for the images in the other script.
Oh, well, there's some weird thing going on here. So just for the purposes of moving on, I wonder if it's being. I imagine this is just caused by the. No, I'm looking at this, I think, and I just can't see it. The issue is it's telling me that those files don't exist. It didn't take very long to download these files, so I'm gonna just nuke them all, get rid of them, refresh. They're all gone, and then I'm going to re-download them, and hopefully this time they work. Oh, so okay, they're too small. So something is happening here, which means that for whatever reason, these files aren't getting downloaded. And that's not something that's not part of the script. That's something that I don't have control over, unfortunately. It looks like, unless anyone has any smart suggestions. Those files, they exist on my Google Drive, so I can just. I'll tell you what I'll do. I don't know why. I think it's just some glitch with either Google Colab or with Google Drive at this moment in time. So what I'm going to do is just load them in from my computer, because you can upload files to this. So I'm just going to go and find those files on my computer quick and upload them, so I'm able to do it. While I do that, has anyone got any good questions for me? Apologies for this, I was not anticipating this. Those files should be 5 megabytes, and they're not. They're only a few kilobytes, so something happened. I don't know where this stuff is. Okay, there's...
Sorry, Dan, quick question.
Yes.
I'm not typing in the chat because I'm actually watching on my phone, and it's too awkward for me.
Oh, okay. Yeah, go ahead.
Just how long are these notebooks going to be available for us to use and play with?
Oh, they'll be available until they become obsolete.
Ah, okay.
I'll keep them up there.
All right, perfect.
Yeah.
If we make a
that's
copy,
sort of the point.
we can play with
Yes,
them.
please. Yes,
Yeah,
make a copy. I strongly encourage you to. There's a lot of difficult material in here, so this isn't the sort of class that you're going to walk away from feeling like an expert. But I think my goal here is to expose you to these workloads, really to enable you to replicate them yourself, but also to to sort of give you an indication of what sorts of things and the types of workflows that are common with this type of work. That doesn't mean that there's not some idiosyncrasies in the way that I have done this, but yeah, as I said right at the start, it's going to take you it might take most people a few run-throughs to really understand a lot of these difficult concepts. I don't know why this is happening. So files should just load in, but they're not for whatever reason. Is everyone having the same problem as me? So it's telling me that they're 5 megabytes. Let me see if I can just do this. Apologies for this. It was going so smoothly too. Let me just see here if I can just read one of these files in, because otherwise we're not going to be able to do the rest of the lesson. Live coding.
Works for me.
Compiler, and then I give it a loss. So you have to, in order to work with the model, I think I mentioned this yesterday, but in order to work with the model, you have to compile it. Even if you're using it in prediction mode or transfer learning mode, you still have to compile it. It still needs to know what metrics to pay attention to. Okay, so metrics. Oh, what am I doing? Optimize. Oh. Okay, so then the next thing I should be able to do is model load weights, and then error escapes. You can see how bad I am at typing now. Okay, So I'm sorry, guys, but I cannot see what the problem is here. I see that file. It has it doesn't have the right size. Something weird's going on here. All right. Well, just for the purposes of getting through this, apologies. I honestly have no idea what happened there. Those files should.
I can share my screen because they ran and you could walk through it.
Well, it's okay, Chris, because I've already got it. I can do that too here because I've already got the output. But thanks anyway. I think I'll just keep going here and plow through. I will, of course, I will troubleshoot this immediately after I get off call. So it shouldn't impact too much. But what I'm doing here is I set that up in such a way that it was going to load 6 different models for 6 different classes. It was going to compile them and download. But what happened is that I can't seem to load a version of those weights that seem like they're fully loaded because they're not the file sizes, and it's complaining at me because it can't find the file signature. But let's assume that those models were uploaded the right weights. Then this is just an exercise here of just reiterating what we did at the start of yesterday's lesson, just sort of seeing what that looks like, how to plot it, what labels we have. But this part here, this takes a very long time, which is why I commented it out, because I didn't anticipate having enough time in class. Turns out I was right. But what this does is essentially it just cycles through each of those models that have had the weights loaded in. So they're now useful for prediction. And it's just using that same piece of code that we used previously to create a test generator to evaluate the number of depths, and then just to evaluate the entire depth. And so what I got when I did that, this is the output that I got when I did that. So you can sort of see these the output for 6 of those 6 different classes in this order. So vegetation was about 97% correct. Background 94. These 2 classes here. Oh, sorry. This class here and this class here were. So that was obstacle and sky, and then road did pretty well. So in general, there's a bit of a mixed bag here. That's good because we want to demonstrate a specific principle at the end. But we've got very strong classifiers. A few of these, I sort of can't anything above 8% good, and so 4 out of the 6 are pretty good in that regard. But we're going to combine those 2 together and then use another machine learning to actually try and figure out whether or not there's some improvement on every specific inch. And the algorithm we're going to use for that is all right. And I can't run these cells, but I can tell you that this is one where I've just loaded in a sample image, and I want its original size, and I'm just cycling through those models and making prediction for each model, and I'm storing the prediction and the ground truth resized downsized in the actual size into 2 separate lists, into the M list, which is for the model, and the T list, which is for the ground truth. So M stands for model in this case, T stands for truth, and it's using each model to predict each class and creating a separate binary mask. So what we have is then a stack of these binary masks that we need to somehow combine into our multi-class segmentation, which is going to solve. And in order to flatten this stack of masks, we just simply sum over the first stack, and that's just going to essentially take all of these binary masks, which are just 0s and 1s, and it's just going to sort of condense them down. But that it's going to give them different values because I use this counter up here. So I'm basically cycling through this. I've initialized the counter at 1, and so 1 is now vegetation. Next time it comes back through this loop, counters on 2 and that background, and that gets assigned 2 to those pixels that are background, 3 to construction, 4 to 5 to rest. And so in the end, then you have this sort of this array that's just values between 1 and 6, but it might not be integer values because there might be the same class may have been predicted. So that's the situation we to deal with. We don't want there to be 2 classes per pixel, so we need there to be a secondary process to sort of go through each image on a task basis in order to evaluate how likely either of those 2 classes work. So if you have a certain pixel that's called one thing, then that's not a problem. It's consistently called that thing. But if you had another pixel that's called 2 or 3 different things by 2 or 3 different models, then you need a sort of a different process to sort of tie the room together at the end. And that's what I'm demonstrating here, and that's what the conditional field is for. So and I'm doing I'm deliberately resizing stuff because, well, partly because the model was, as we know, it was trained on 512, and it would be upsized into its original size, and that's common. But the artifact of the implication of resizing the labels is that you might get some interpolation, strangeness in those areas resized near the boundaries of labels. So this basically goes through a process of seeing, okay, what does that look like in its sort of raw form? And you can see that there's a lot of sort of high frequency noise in these labels near the boundary because of that resize that's gone on. It got resized down to make a prediction, and then we had to resize it back up again in order to make the to get it the same size that we want. So one strategy, a simple strategy, a common strategy you're probably familiar with, is to use a filter. You would just use a filter to pass over that and sort of smooth out some of that high. So we're interested in preserving the actual those best can. But it's a fairly naive approach because we don't know what size to use, and that size might actually be different, ultimately different image. Especially if you've got a different perspective, but also because of just the very specific nature of how boundaries might how classes might interact their boundaries. So that, the median filter that I've implemented here, I just took a number 15 and it seemed to work okay for that image. But I guarantee that number wouldn't necessarily work equally well for images. And really, it's not a very sophisticated way of dealing with the problem because it's not learning anything. It's just smoothing over where the labels are. But so a better way to deal with this problem, in my opinion, is the use of this conditional field. And that sounds like a very complicated thing, and it is, but it is a very powerful that gets you that's very useful post-process or model application for both binary and multi-class citation, and for models other than UNet and model approach other than merging by class. So, for example, many of the state-of-the-art neural nets out multi-class citation, they have some form of a conditional random field in their process. That's often the very last thing that it does in order to just tidy up that segmentation on a task by task, or a task specific bit. And what I mean by task is a single image. So what it takes is it takes your bad labels, which could be your ground truth if they've been resized, or it could be your model output if it has some error, and it tries to figure that out. It tries to relabel those portions of the image that have been labeled incorrect. And the way it does that is by basically producing it uses a machine learning algorithm to figure out what the likelihood of a class given the image is. There's many details about this algorithm that I don't now have time to explain, but I will encourage you to read the paper I wrote a couple of years that really demonstrates how powerful a conditional random field approach is for cleaning up and these types of data. And the reason why it's so powerful is because it uses both. It takes your label and your image. It creates a probability distribution that is a generating probability distribution. So it's able to evaluate pxy, the joint distribution of the image and the labels together. And it does so by essentially passing a kernel across the image that evaluates the spatial structure of the image features with respect to class, and also the color structure associated with of every class. So it's a very powerful model, and the math behind it is very complicated, but that doesn't mean that we can't use it if we don't understand what it's doing. It is controlled by a few parameters that end up being hyperparameters that we have. And I've given you some numbers in here that seem to work pretty well for most. So I would encourage you, if you are interested in this, to start with that paper and other papers that you issue, and then start with this function to explore this idea. But also be prepared that these parameters might actually change depending on specifics. And apologies for having to do this quite fast, but I did want to get the end. So what we're looking at above here, this was just a few examples using median filter, and I wanted to sort of contrast that against the same thing but using conditional random field instead. And so what it's doing is essentially passing these kernels over the image, essentially generating probability distributions that convert features in class, and then uses that to sort of evaluate how likely every label that we have given, and it may make a decision to unlabel and relabel if it feels like that's mislabeled. And that's a very powerful thing, both for cleaning up the segmentations that might output of a model, but it also conceivably is a good way to clean up your label first. If you're going through the process of manually annotating imagery polygon, you might consider using a model like this in order to actually generate fine scale frontage, but that's going to be something about R class. So here I'm running through, and I'm essentially running this function which is implementing this conditional random field on every predict label and also every true label. And I'm doing it on the true labels because there could be some error in those, but also for the most part every side has her. And you can see that in the end it does at dealing and combining the labels in such a way to evolve or set thresholds or do anything super specific in the decisions that go behind combining labels. So that was a super fast run through of that tutorial because we spent more time previous one, but hopefully I may have lost a few folks on the way there, but hopefully this is something you can circle back to. You all have my email address. I'm very happy to answer on topic. I am going to keep these two websites going, as I said. I'm going to return to the questions now on the chat just for the last few minutes here before we have to wrap up. But if you have any questions about anything, then please let me know. Oh, actually, I should mention, so you can, if you don't know this already, you can download these as Python files or as IPython notebooks or Jupyter Notebook. You don't have to run these on Polar. You can download them and you can run them on your own machine. If you need help with setting up the environment, then I can sort of email that around RFAC or even our presentation to explain that. There's a lot of detail in here. This isn't necessarily something you're going to have full grasp of right now, but I was more concerned about giving you something that really worked and to build on. So even if your Python skills aren't sufficient yet to understand everything that's going on here, and if your understanding of machine learning is sufficient to understand everything, hopefully I've at least demonstrated that these sorts of things are possible, and hopefully you're able to take workload and you. Okay, so I'm going to go over to the chat real quickly and see if anyone got any questions. Yes, restarting my kernel was a good idea. I think got till too late. There is a recording. I've linked to some resources in the website that you can start from, and they have links and textbooks from them. The website I'm talking about is these websites. Let me see what else we've got here. We have to downsize the images because they have fit on our hardware. So hardware in this case GPU. But if you had limited RAM, then your CPU would struggle too. So that's the main reason. It's really just dependent on the specific power. GitHub, yes, there is a GitHub repository. I can send that around. So these websites actually they are GitHub repository. They're GitLab because GitLab does a better job. Traditionally, you've done a better job of continuous integration. So I could just push changes to this and it automatically updates that. But I'll send that around. And Chris asks, if there's an environment.yaml file? There isn't, but I can certainly make one and share that. And I'll end up probably just adding a last page to this website that has that downloading or has that donation. But we're now at 2:00, so I think we're gonna have to call it. Hopefully you got a lot out of that. Please stay in touch. Thank you so much for joining me today and yesterday. It's been a blast. I'll stay on the line for a few minutes as long as CSDMS allow me to, and I'll continue to answer questions that you have. But I imagine at some point Chad is going to just drop. He's going to kick me off, at which point we're done. But thanks so much, everyone.
Thank you, Dan.
Thank you, Dan.
Thanks,
Great
Dan.
job. Really nice.
Yeah, good.
You're
Really
very
good.
welcome.
Thanks. Bye-bye.
Hey, Dan.
Hey.
I'm just curious if there's any way to look into any kind of inference that the model is doing and how it's making some of the classification decisions, because it seems like we're losing some inference.
Yeah, absolutely. I mean, what we've done here is a 4-hour deep learning class that could easily be 4 days or even 4 weeks. And so some of these things I've obviously brushed over, but that's a great question. So I'm going to go to my browser here. Oh, you can't see the screen. The technology that you're after is called class activation map. And what it does is it shows you a heat map of where the So if you're looking at trees and it's classifying as trees, then your heat map should show up relatively high value. We didn't have time to cover it class, but there's a number of characterizations.
Okay, cool. Yeah, I can do that Googling.
Yeah, so look up CAM, class activation mapping, and GradCAM, gradient class activation mapping. And it sounds really complicated, but it's not really. It's not super complicated. It's not very complicated to implement code.
Awesome. Thank you so much again.
You're welcome.
Hi, Dan. Thanks for the lecture. Really enjoyed it. So question, can we actually apply these UDATs to classify different vegetation types, like with multispectral images, so not only RGB?
Yeah, you could adapt this to multispectral images. So you'll see in all of the lines of code where we actually initiate a model, we've got the size, right? And the size we used was 512 by 512. And then I added 3 to the end, right? And I added I added 3 bands to my model input because I had an RGB image, so 3 bands. But if you had a 4-band image, you could just add 4 and it would do the same. Or if you had a 5-band image, you could add 5, do the same. I'm not going to say that it will work the same or function the same or have the same accuracy or anything like that. That's going to depend on data, but and your class at various other factors. But in theory and in practice, there's so many examples of that. If you look inside the remote sensing literature, search for hyperspectral unit, you'll already see that a number of people have made that.
Cool, that clarifies. Thanks.
You're welcome.
Alejandro has 2 questions, and they're in the chat.
Oh, okay. Sorry, I did those. Different size, right? Yeah. So if you've got these big format images, then for sure you have to chop them up into so they're the same size. Subdividing into small windows. Yeah. So I think that's how you deal with it. Oh, right. And apologies. Yeah, I was meant to get back to the lumping and splitting, but obviously my technology failed right in the middle of it. Yeah, that is the golden question right there. That is very difficult to answer. So the question is, do you lump, if you have classes that are the same, do you try and lump them together, or do you try and maintain the split best you can? And unfortunately, that really does that really does need experimentation to try and figure that one out. I've gone through this many times in my own research, where the initial set of categories that I thought were going to work well ended up having to be modified based on initial trial. So I'd go through the process of labeling using those images, using those classes. I generate a small set of labels, and I would train a model just to see how well it might do. And at that point, it becomes clear that you maybe have to combine similar classes. They're being mispredicted. In general, I think you're combining more than you're splitting, but it really does depend. I think it really does depend on your data and how resolved those features are within the data, and how different those features are among classes. If you have 2 different vegetation types that are basically exactly the same, then if for all intents and purposes, they have the same range of colors, they have the same general texture or whatever, then it's going to be difficult if there's no really strong spatial spatial zonation signal in there, or any really other sort of covariate that it sort of use in order to make that call. A lot of this stuff as well, like I should say, is it's as much an art as it is a science. You have to, it's numerical modeling, but it's in a very different way than you may be used to, and you do have to develop an intuition over some of these things, and that really does come through experience. But especially when it comes to whether or not you lump or split classes. I hope that answers the question. That's the best I can do.
I think it does. And I see Will has another question also in the chat.
The variation of your size or perimeter complexity matter with your labels? Yes, it does. The perimeter is obviously a big one because it needs that's the hardest place to actually label, right at the boundary of two things. Because that boundary, the location of that boundary and the crispness of that boundary gets modified by the model. So your features have to be spatially strong enough to deal with the fact that you have the two adjacent. And the size matters because of the class imbalance.
Thanks. So I don't know if my mic is on, but so with the size, then is it good to sample across a range of sizes? Like, let's say you've got sediment, different patches of sediment of the same composition that are different sizes. Presumably then you want to capture all of that size range as part of your labeling process?
So what do you mean exactly? So the size range, the size of the image, or the size of the?
Oh, sorry, the size of the sediment patch. So if like say I work with gravel bedded rivers, but sometimes you get in certain environments you get ephemeral deposits of fine, and they might be 2 square meters or they might be 50 square meters. So as far as defining your labels, then do you want to try and capture that size variation with your labeling?
I guess I still don't quite follow. I mean, I definitely see a situation where your gravels have been filled, but I don't understand what you mean by the size of the label. Like what you're labeling is whatever size it is, you're labeling it, right? So do you mean the image resolution? Oh, the polygon. Yeah, well, you'd want your polygon to be the same. You'd want your polygon to completely cover the entire thing that you're interested in. So in your case, gravel, you'd want your polygon to cover the entire gravel pad. In your case, though, it's going to be more, distinguishing between different grain size is going to be tough because of all of the downside of the image. So you'd want to split your image up. If you had a big, large image, I think you should just split your image up into smaller images, but you preserve the size of the actual size pixel. And then when you're labeling on those tiles, and you can either decide, if the tiles are really small, you can either decide to just give it a single number value, like that's gravel, that's sand, that's silt, gravel, that's sand, that's silt, or you could actually go through and do the polygonal label on those smaller tiles. But if you want, send me an email and we can pick this up over an email conversation.
Yeah. Sorry to tie it up. Yeah.
No, that's okay. I just don't know how long Chad and Albert here have got. That's all.
I got one question, but I see Alejandro has one more question about splitting images and if you need to have an overlap on those tiles.
Right. So as I said, you probably missed it because I was saying it quite fast. But a good strategy is exactly what you're saying, to split the images up and the labels up such that there's a big amount of overlap, because then you've got more to deal with. You've got more computation that you need to do, because if you've got 50% overlap, you're essentially doubling the amount of work that you need to do. But as you say, the edges used with the labeling, if you have multiple versions of that label for every pixel, then you've got more information to make a decision with.
And I don't want to hold you up too long then.
No, it's okay.
This was awesome, and I've always want to get more into machine learning. So maybe this will push me over the edge in doing so.
Yes.
I'm interested in detecting water, which is pretty easy, I think, only for satellite imagery. So we've done some simple stuff on MODIS, but I want to use spheres, for example. And I was wondering if there are some good labeled data sets out there already for satellite data that you can point me to.
For water? Yeah, there is. Yeah. There's a lot. Let me have a look here. I can't remember exactly what it's called. I tell you that. So I can tell you that these models work well. I put together a class late, and that worked pretty well from Sentinel-2 imagery.
Yep.
I also know that I've used this model it's quite effective at pulling out, for my personal research, I have to pull out the land from the surf zone from the ocean, sea. So it's pretty good at pulling those out as well. So that's a form of water detection. I'm just trying to look up here. I'm trying to find a link to something that I found that it was essentially a global water polygonal data set. Just trying to find it.
Because in the end, what we would like to do is, every day there is somewhere on Earth flooding, and right now there's in Michigan because there was a dam breach, right? And there's this cyclone hitting Bangladesh. So we want to capture those events and provide flooded area or flood extents to the various relief agencies. And we do that right now already, but I think we can optimize it. So I want to do it for optical data, but in the end, I would love to do it also for radar data as well. But that's a whole different category, I think.
Yeah, I mean, I think, apologize, I can't find this data set. I do have a copy of it. So if you send me an email, maybe I'll just send you the email later on. But that's what you need. But then going back to what you're saying, I think I'm fairly confident that this model would get you at least most of the way there for detecting water. I'm not too sure how well it would transfer, between different types of satellite imagery, for example. Like, there's like different bands or different sensors. Yeah. But I imagine that it would work pretty well. The case describing. I don't know about really super specific cases like really optically clear water or very shallow water, or but I certainly imagine deep pools of water that are optically opaque. I imagine this is going to work pretty well.
Okay, that's cool. Yeah, and definitely water. There are certain areas in the world where the water is so sediment rich that its color is towards brownish instead of the dark black, and that it might
but even in that case, so when I put together a course that looked at lake detection, there was a lot of muddy lakes and a lot of really dry lakes, a lot of drying up lakes, the Aral Sea and places like that, which the color signatures of all of these different lakes across the world were very, but the models still managed to be able to reliably tell and I don't know if that necessarily transferred real extreme members of like water bodies like hypersaline lake or hyperturbid lake, hyperturbid rivers, but I think for the most part.
Cool. Okay, I will follow up with an email. Yeah,
okay, cool. That
great.
sounds good.
This was awesome, Dan. Thank you very